Oh. If you were not awake, now you are awake. So thank you for, after a long and intensive conference, thank you all for coming here today. It is my pleasure to introduce the inaugural Cox lecturer today. So as regular participants of the conference will know, IMS used to have one more lecture than Bernoulli. And my colleague, Victor Panaretos, realized this as Bernoulli president. So in the lecture arms race, he proposed a new one. So after the eminent late David Cox passed away, he suggested we should add a Cox lecture. And we now have the inaugural Cox lecture here. He's going to tell us about omitted variable bias. Viktor Chernousokov is the Ford International Professor at MIT. He's a professor both of economics as well as affiliated with the Center for Statistics and Data Science. He is an alumnus of Illinois Urbana-Champaign as well as Stanford, and he's faculty at MIT, a fellow of the AAAS, Hannan Lecture, another inaugural lecture, the Cowles Foundation, and I could go on for a long, long, long time. So we're extremely pleased to have you here, and rather than me giving background, please tell us about omitted variable bias.
Yeah, thank you very much for the introduction. This is going to be a presentation of joint work with Carlos Senelli, Whitney Newey, Amit Sharma, Vasilis Serganis, of the paper that we put in archive maybe more than 2 years ago. And more recently, we've also produced the software both in Python and R. You could ask me why am I presenting a paper that is like more than 2 years old? And the answer is I was on medical leave. I'm still on medical leave, doing like every month I have to do chemotherapy. And so given all of this, like I'm extremely happy to be here, extremely happy to enjoy this conference and see this World Congress, which I enjoyed in the past as well, like very much so. And I really much enjoy the Bernoulli Journal because it's unapologetically technical, unlike the Annals of Statistics that shifted towards a general interest, right? Just a little joke, yeah. So yeah. Anyways, so let me just motivate a little bit the talk with a historical precedent that goes back to like 70 years ago. When in the late 50s, people observed a very strong association between lung cancer and smoking. So in particular, it was noted the risk of developing lung cancer for smokers was 9 times higher than the risk for non-smokers. And so it obviously suggests a very strong association, but is this really a causal effect, right? Does smoking cause cancer? And at the time, this generated a very lively debate between very prominent members of the profession. Ray Fisher, on the one hand, representing both the the powerhouse of statistics as well as the tobacco industry, and being the avid smoker himself, he argued that obviously smoking does not cause cancer because there could be some latent gene or hormone that could generate both, that could induce smoking behavior and also induce the cancer. At the same time, Jerome Kornfield, who is a prominent biostatistician, and he was also the president of the American Statistical Association in the 70s. He created a team of statisticians and bioscientists that wrote up like a long paper that presented the opposite story, and they argued that this argument that the Fisher provided is certainly it's mathematically correct, but it's implausible. Using both the medical context and simple quantitative reasoning, which was used to bias, bounding the bias. So in particular, if I have to paraphrase their finding, I would just in one sentence, it would be something like this: like for the smoking not to be a causal effect, not to have causal effect on lung cancer, the proportion of smokers who carry this A hormone or this latent gene has to be 9 times greater than the proportion of non-smokers that carry this gene. And they said, well, like we don't observe this, it may still be the case that there's this latent hormone or this latent genotype, but at least for the observed hormones and for the observed genetics, like we don't ever see any striking differences like this, right? And so they argued that this is the story that Fisher told is implausible, and this finding was generally accepted by the medical profession. And obviously, one way to settle the debate would be to run a randomized control trial, but that's clearly insane, right? Because it's hard to, it's just for a number of reasons, right? So sometimes we have to rely on observational data to make causal inferences. So what do we do in this paper? So we provide one approach that is very simple and at the same time is sharp, that allows us to examine the size of the emitted confounder bias for a broad of causal parameters, and this is all for general non-parametric models. So in particular, we could analyze the cases like this lung cancer example, but we can analyze a fairly broad setup in this framework. So in particular, the list of causal parameters of interest that we cover includes such objects as average potential outcomes, for example, policy values, average treatment effect, including subgroup effects, average causal derivatives, average effects from transporting covariates, average effects from distributional changes in covariates. And I could continue and say that as long as the parameter of interest can be represented as linear functional of the so-called long regression function, our framework applies. So what do I mean by the long regression function? It's a regression of an outcome on a treatment and observed and latent confounders. So if we observe the latent confounders, we could run this ideal long regression and obtain causal conclusions in this way. My apologies. So and then we can define the parameters as functionals of this long regression function. So what we show is that the size of the emitted confounder bias depends on the additional variation that the latent confounder creates in the outcome and in the treatment. And it's formally the latter is captured by the variation in the Ritz representer for the parameter of interest. So this is a technical bit that gets into this picture. Now, imposing hopefully contextually motivated bounds on these variational gains generates the bias bounds and allows us to obtain the bounds empirically. We also provide efficient statistical inference methods on the bounds using the debiased debiased learning ideas that are based on modern statistical data adaptive statistical methods that are labeled these days as machine learning, right? So in particular, we would have to rely on machine learning of regressions. Okay, we are very familiar with that, but we also provide the tools for machine learning of the Ritz representers. And I'll mention how we do this. So to set up things formally, let me use a structural equation modeling as a language. So here, so it's kind of like one of the classical languages for speaking about causality, and especially popular in computer science and econometrics. So here, so we have an equation. We have an equation for the outcome variable y. It's determined by the treatment or policy variable d. It's also determined by the observed confounders and latent confounders a. And then there is also a stochastic shock vector of stochastic shocks that generate generates the y. And then these g's are called the structural functions. Then you have a similar equation for determining the treatment. The treatment is determined as a function of observed confounders, latent confounders, and the stochastic shock, and its own stochastic shock. Then you also have equations determining the observed confounders and the unobserved confounders. And the stochastic shocks here are independent across the equations. So that, of course, corresponds to this directed acyclical graph that you're seeing. This is like a very simple form of a DAG. So this structural equation model induces potential outcomes. So sometimes people start with potential outcomes. So here we start with the structural equation models and say we get a potential outcomes from the interventions, right? So we take the intervention and we replace the actual treatment variable by a fixed value d, say 0 or 1 or something else. And that induces, like in the first equation, and that induces the potential outcome, right? And then, given the independence of the stochastic shocks across the equations, we can immediately obtain the following conditional exogeneity or conditional ignorability condition, namely that the potential outcome here is independent of the actual treatment assignment, conditional on X and A, conditional on observed and latent confounders. So if we observe both the X and A, then we have a randomized experiment, right? So the treatment is assigned independently of the potential outcome. So in principle, I could have started with just equation 1.1. And if you're familiar with potential outcomes, that would be the natural starting point. But for many people, like I would say, a lot of people are not familiar with potential outcomes, coming from different schools of thought, and starting with like structural equation modeling. But in a way, it doesn't matter. Like all the roads lead to Rome. So like 1.1 is the equation that is derivable from the modeling, from the causal modeling assumptions that we make. So in principle, equation 1.1, the ignorability condition, is also derivable from a variety of other structural equation models. So in particular, we could have latent variables or latent confounders showing up in different parts of the DAG. We could also have the x's being the measurements of this latent variable a. So think about like ability in the context of analyzing the effect of education on earnings. So x1 and x2 are like measures of ability, like SAT scores, IQ tests, and things like this. Any of these models, they imply equation 1.1, doesn't matter. So, and in principle, the bounds that I'll show you, they only rely on equation 1.1, okay? So once we have the equation 1.1 in place, we observe that, well, that the long regression function that we obtain by regressing y on d and x and a, that's the ideal regression that we can run. It's going to recover the causal object, which is the conditional expectation of the potential outcome conditional on x and a. Right? So that's a standard identification result in the literature, and then we will denote this long regression function by G. Right? So that's the ideal setting. And then in this ideal setting, we also can say, okay, so we now we can recover this. This is the statistical object. This is the causal or structural object. We can summarize the causal object by for example, the average causal effect. So we could say maybe our parameter of interest is the average difference in the potential outcomes, which is identified by the average difference of the two long regression functions. Right? You turn on the treatment to be 1. You compute the regression, or you turn on the treatment to be 0, compute the regression, take the difference, average out. That's a parameter of interest, causal parameter of interest. So that's for the case of binary D, and for the average causal derivative, which is of interest when D is continuous, we could look at the average derivative of the potential outcome, which is identified by the average derivative of this long regression function, right? So these are the two running examples that I'm going to use. There are other useful examples. For example, the average incremental effect. Suppose that D, the treatment variable, is a count variable, such as the numbers of years of education, then we might be interested in the effect like this, right? Suppose we increase education by a unit, and we ask, like, okay, what's the effect on wages, right? So that's going to be the average incremental effect, and that's also identified as a linear functional of this long regression G, right? Yet another useful example is the average policy effect from covariate shifts. Let's say a policy shifts the distribution of covariates, then we integrate, we're interested in what happens to the expected value of the potential outcomes under the distributional shifts in the covariates. And this is also identified as a linear functional of the regression function. And this object shows up a lot in the decomposition analysis, like Kitagawa, Osaka-Blinder decomposition analysis that are very widely used in social sciences and economics. And there are other examples, as long as they are linear functionals of the long regression functions, it's covered in the setup. Of course, the problem we're dealing with is that these latent confounders are not observed. The vector of latent confounders is not observed, and the question is, what do we do in this case? So obviously, we could still run regressions. And in particular, we can obtain from the data, we can obtain the short regression. We will denote it by G sub S, and this short regression is going to be the projection of the long regression on just D and X, right? L2 projection on a smaller space, right? Now, given the short regression, we can compute short parameters or proxies. So this is going to be short parameter or approximations for theta. So in the running examples, like for the average causal effect, we will take the average difference between the two short regressions. For the average causal derivative, we will take the average derivative of the short regression function. And what we want to know is that what is the bias? What is the bias? What's the difference between the short parameter and the ideal long parameter theta? And using this the bias formula, we would also like to place bounds on this difference, as well as perform the statistical inference on theta and using modern learning tools. There is a long literature on the topic, obviously motivated by initial study of Jerome Kornfield. There was foundational work by Rosenbaum as well. But our story is going to be short, so we will provide one framework that is more general, covering a whole class of examples. It's going to be non-parametric. It's going to be simple, so in the sense that, I think it's very simple to teach, and interpretable, and also sharp, right? So, and then we also provide statistical inference. Namely, we give the confidence bounds for the bounds on theta. So to present the results formally, let me describe the general framework. So we have this. I'm going to use the notation W for the long list of regressors, and then WS for the short list of regressors. We will say that our target parameter has to be expressed by this formula 1.2, where M has to be linear in G. The formula has to be linear in G. And also we need the continuity with respect to G in L2P norm. So the running examples that I gave so far, they trivially satisfy the linearity property, because the M formulas are linear here. So this is obviously linear in G. This is linear in G. The continuity condition is less trivial, and it is satisfied by what one can call the weak overlap, like weak overlap conditions that are spelled out in the paper. So. Another assumption it's about the short parameter. So, like the requirement here is that the short parameter must be given by must be defined by the same formula where we are replacing the long regression by the short regression, and also we need the M formula to simplify. So we need once we plug in GS, the short regression, in the formula. The formula only depends on WS. So this is trivially satisfied in the running examples that I gave. So under these assumptions, we're going to write we're gonna derive the emitted variable bias formula, and provide the bounds on the bias as well as statistical inference method. And the key to the result is going to be the Ritz-Frechet representation. So this theory, the representation theory, will tell us that there exist unique square integrable random variables, alpha of W and alpha S of WS. The long and short Ritz representers, such that the long parameter and the short parameter can be represented as the inner products between the regression function and the Ritz representer. Okay. Moreover, the short Ritz representer is related to the long Ritz representer in the same way as short regression related to the long regression. It's the conditional expectation of the long regression given the short list of regressors, right? So this is the inner product representation. You could also think of that as a kind of reweighting representation for the parameter of interest, because you could take this G of W and by low iterated expectations replace it by Y, the observed outcome, and then you see, okay, what this representation is doing. It's providing another way to characterize the parameter by simply as a reweighted outcome. And so this may or may not be familiar. In case it is less familiar, the following examples are helpful. If we have, let's say, probably the simplest and the most classical example is going to be the first one. Let's suppose that both the long and short regressions are partially linear. So yeah, partially linear things are nice, right? So you have this, the treatment variable enters linearly, other things show up non-linearly. So in this case, in a partially linear model, the average causal effect and average causal derivatives, they coincide. And then we have that the Ritz representer in this case is given by just a residualized treatment. So you take the treatment, you subtract off the predicted value of the treatment given the list of regressors, and then you scale by the second moment. So if you look at this instance, you'd say, okay, this looks like the Frisch-Wall-Lavelle theorem, right? So indeed, the Frisch-Wall-Lavelle theorem, like for representing the parameter theta, is just a special instance of the the Ritz-Frechet representation theory, right? So yet another classical example, so for the average causal effect in the binary treatment case, the Ritz representer is given by the Horwitz-Thompson weight, right? So we have the indicator of treatment hitting the treatment states, normalized by the probability of visiting those states, and because we want to retrieve the average causal effect, we take the difference here. And one can verify that this is indeed the correct representer using the change of measure arguments. And this is like Horwitz-Thompson like reweighting approach to recovering the average causal effect. Again, this is a special case of the Ritz representation theorem. So for average causal derivatives, one could say, oh, like the Ritz representer is given by the logarithmic derivative of the conditional density function of the treatment variable given the regressors x and a. And this is derivable through like integration by parts and all that. It's also interesting to note that the short representers here in all the formulas, they are obtained by just dropping the a in the formulas, but they can also be obtained by computing the conditional expectations, and the two ways they actually coincide for these examples. I could maybe provide more analytical examples, but actually, it turns out that the analytical derivation of these Ritz representers is not necessary. We could use variational characterization of the Ritz representers that requires us only to know the formula M, the formula that defines the parameter of interest. So in particular, the Ritz representer solves the following problem, where you minimize the second moment of the candidate representer, and you subtract off this expression 2, then you take this M formula and evaluate it at A instead of the regression function. And to see that this retrieves the Ritz representer, you can set up the first order conditions for this optimization problem, saying like, okay, I need the derivative to vanish in all directions. And you'll see that this first order condition gives you the definition of the Ritz representer. right? And so we use this formulation to set up learning of the representers using the lasso methods, neural networks, and random forests. Like we have results for three. We have both the theoretical results and the implementation for three different ways of learning these representers. And what's nice about this characterization, it only requires us to know the formula M, no case-by-case analysis, and it tends to produce better behavior estimators for the representers than the plug-in approaches. So, for example, like, okay, if I know this formula, I could use this formula for estimating the Ritz representer, but here I need to divide by the estimated propensity score. And this could not work well when these propensity scores get close to 0 or 1. At the same time, here, like you rule out the explosive values of A by the very nature of the optimization problem here. So this tends to produce better behaved estimators of representers in practice. Anyway, so that's the key lemma, and then given this key lemma, 2 lines of algebra give the following result. They give the result which states that the emitted variable bias is equal to the covariance between the regression error and the representation error that result from omitting the latent confounder. Okay. So just using the properties of the lemma, we obtain this result. And furthermore, given this covariance representation, it's trivial to obtain the following bound. So we can write we can take the square bias, write it as rho squared times b squared. Rho squared is going to be the r squared between the regression error and the representation error. And then b squared is going to be the product of the second moments of the two errors. And of course, this is upper bounded by b squared. Moreover, this b squared, the upper bound, is always attainable without further restrictions, because in the non-parametric settings, we can always think that the regression error, so we never observe G, right? So the regression error could be proportional to the representation error, right? So we don't observe this long objects G and alpha. We don't observe. So in principle, nothing can rule out this proportionality. And so once things are proportional, then you hit this upper bound, right? So this is sharp. Without further constraints on the problem. And yeah, and what's also nice about this, it generalizes the classical omitted variable bias for linear models that we like some of us who teach linear regression. We often teach the omitted variable bias for linear models, and this nicely relates to that. So we can do some further interpretation work. We could say, oh, let's let the r squared v tilde u denote the r squared from linear projection of v on u. Then we can rewrite the upper bound as the scale parameter times cy cd all squared. So this s here is going to be scale of the bias that is learnable from the data. So it's the second moment of the residual. This is the second moment of the Ritz representer. These factors here, cy and cd, they measure the strength of confounding. So this measures the strength of confounding in y. This measures the strength of confounding in d. And these have to be restricted by the analyst in empirical work, given the context. The R square in this formula here, so R squared measures the proportion of residual variance in the outcome that is explainable by the latent confounders. And this factor here measures the proportion of the residual variance of the long representer generated by the latent confounders. So yeah, while this is familiar quantity, this may be unfamiliar, but luckily, if you look at the examples that I gave, in each of those examples, this quantity reduces to something that is conceptually very tractable, either like adjusted Pearson R squared, or relative gain in precision, or relative gain in location information, depending on the model, right? So this is arguably, this quantity here is interpretable. Right. So far we've obtained these bounds of this form. Upper or lower bound is equal to the short estimate plus minus the scale times CY times CD. So these components are restricted through the context, right? So we restrict them through hypotheses that limit strengths of confounding. And these components, theta S and S, they have to be learned from the data. So this is short parameter, has to be learned from the data, and this S has to be learned from the data. And for learning these parameters, we will use the following representations. So for the short parameter, we will use the natural representation plus a correction term. You have the residual here multiplied by the Ritz representer. For learning this, we'll just use this formula itself without changing it. And then for learning the second moment of the Ritz representer, we will not use this formula. We will use instead this formula, which is the value of the objective function that the Ritz representer optimizes. So why are we using these representations that are not the natural ones, but well, we use them to obtain the local robustness or Niemann orthogonality property, namely that if we look at the equations that define the parameters of interest, we see that with these formulations, if we perturb the values of the nuisance parameters around their true values, the first derivatives vanish, right? So the nuisance parameters are the G, the short regression function, and alpha S, the short representer. Like, we're going to be perturbing. It's like we don't know these parameters, so we have to do the plug-in, right? So we work with perturbed values, and these formulations, they ensure that the first order biases are eliminated in this way, through this, right? So this is local robustness or Niemann orthogonality property, right? So it goes back to Niemann in the 50s, who used this sort of approach to set up his like the famous C alpha test, right? The projected score test. Anyway, so then, so these are the formulations. So we're going to be basically, our estimators are going to be method of moments estimators that are going to be working with these Niemann orthogonal scores, and we're going to be using cross-fitted non-parametric estimators of nuisance functions. And so this is in fact the builds on this classical ideas in semi-parametrics, going back to Boris Levitt's work and in the 70s, Ibragimov Khazminsky's work in the 70s, Anthony Schick's work in the 80s, and lots of other great papers in the 80s. So and the nice thing about this is that we can use like modern machine learning methods for learning the nuisance functions here, and so. So the estimators here are like that we obtain are going to be asymptotically linear and Gaussian, like the estimators for all of the components. So meaning that the estimators are going to be after scaling by root n, they're going to have approximately linear representation, and central limit theorem will hold. So we have this result under mild assumptions and under assumptions that require learning of G short regression and rate representer to be faster than n to the minus 1/4 rate. So once we have this, then we also have that the plug-in estimators of the bounds, they themselves are going to be asymptotically linear and Gaussian, and with the influence functions that are given by these expressions, which fit in one line, right? And finally, confidence bound. So you take the estimated upper-lower bound, you subtract and add the critical value times the standard error based on the theory, on the provided theory, and that's going to have certain coverage guarantees. So finally, we can put all of this to practice. So I'll just briefly illustrate how we put this to practice. So I'm going to briefly revisit this 401k analysis so it's based on this work by Jim Poterba and others in the early 90s. So 401k program is a private pension plan in the US. So if you work for a university, typically a university offers a possibility to invest money in a tax-free way in the stock market or other financial tools. And so, yeah, the plan was popularized in the early 90s, and we're interested in the causal effect of 401k eligibility on the financial assets, net financial assets. And early on, the empirical workers here, they studied this problem by saying, okay, we're going to control for worker level covariates, and we will claim that we uncover the causal effect in this way, right? And so the underlying thinking is maybe represented by this DAG that you see on the left. So here in this DAG, you could also have firm characteristics in the picture, but as long as there's no edge connecting firm characteristics to Y, this X, controlling for X here, or conditioning on X, is going to close the backdoor path between D and Y, blocking all the non-causal association between D and Y, and only revealing the causal association. You could still have some other latent variables in the picture. For example, you could have latent factors determining firm and worker characteristics. It doesn't matter. So here, just controlling for X works fine. You recover the causal effects in this way, and you get something like this maybe. So the average treatment effect would be around 10,000, and this effect actually varies across income groups, right? So this is the first quartile. This is the highest quartile. In the low quartile, it's 5,000. In the upper quartile, it's 20,000, and these are substantial numbers. So this is just the effect over 3 years, right? So, and then of course, like when I was teaching it, I always thought, okay, this makes to me it made no sense. Primarily because, well, I know that my employer actually doubles my savings. So there's a match amount, like I maybe contribute 10,000, my employer offers another 10,000. So it's very nice, right? Other employees, they might be able to match 50%, some employers don't match, and it clearly depends on the firm characteristics, right? So like there's this M, the match amount in the picture, unobserved, affecting the Y, the firm characteristics unobserved. And so clearly we have the effect from the firm characteristics to Y. And so that's a confounder here, latent confounder. And now we have a backdoor path between D and Y that is not blocked by controlling for X. So then the question, okay, so what do we do about this? So what we did here, like we came up with a particular confounding scenario. We consulted with Jim Poterba, who's a like public finance expert, right, to formulate a scenario. We did some benchmarking. In the end of the day, we took this scenario where we said these numbers, CY and CD, are going to be 4% and 3%. We argue in the paper that this is a conservative scenario, and then using this conservative scenario, we estimated the bounds that are shown in red. So these are empirical estimated bounds, and the blue curves are the confidence bounds for the bounds. And we see mostly the conclusions hold up. We still have like, well, I don't show you the bounds like for the average treatment effect here, but yeah, it's removed away from 0. For the high income groups, the bound is also removed from 0. For the low income group, it's removed from 0. There's some excursion into the negative territory for the second income group, but it's not a big excursion. So, you know, like, yeah, then we conclude, yeah, this is robust. This is robust to this confounding scenario. So, you know, one can do more elaborate, like one can actually analyze lots of confounding scenarios in just one plot. These are called sensitivity plots, where you have on the vertical, so on the horizontal axis, you plot the strengths of confounding in the treatment. On the vertical axis, it's the strength of confounding in the outcome, and depending on the scenarios you pose, you can end up supporting the original conclusions or rejecting them, depending on how strong your confounding scenario is, right? So maybe you didn't like the scenario that I told you, and maybe you would like to entertain another scenario, so you could use the sensitivity plots in that way. So I'm going to conclude. So in conclusion, I want to say that we, in this paper, we construct simple and sharp bounds on the size of the immediate confounder bias for a broad class of causal parameters. We show that the size of the bias depends on the additional variation that the latent confounder creates in the outcome and in the representer for the parameter of interest. And assuming bounds on these variational gains implies the overall bias bounds. Furthermore, we provide efficient statistical inference methods on these bounds using debiased learning ideas that are rooted in classical semiparametrics. And that construction also relies on the machine learning tools for learning Ritz representers that we've developed in the companion papers. Yeah, that's it. Thanks.
Thank you.
Thank you very much.
Certificate for having delivered the first ever Cox lecture. Thank you very much. That was absolutely really, really nice. It's always a difficult question of what do you do when you don't have the data that you wanted to have.
Yeah.
So it's really nice to see your sharp bounds and the issues that we have. We're now going to go to the part where we take questions. So to be able to manage this, we're going to have someone who goes around with a microphone. So you'll need to put your hand up if you have any questions. So that was the gentleman over there, please. And when we get more questions in a second, you'll have to indicate to me when you go first.
Thank you very much for the nice talk. Can you hear me? Because there were some audio issues before, so okay. It seems like most of the work relies on the M function that you're being able to represent, and the question is, can you extend this to other situations where your model is nonlinear, or some other estimating functions that can be also represented by M functions, or have you done that so far? Thank you.
Yeah, that's a great question. The parameter of interest in this paper is a linear functional of the regression function, which itself can be nonlinear, but the parameter has to be linear. Now, the question is, your question is, I think, is can we analyze? Can we provide bounds for parameters that are nonlinear functionals of regression functions? For example, we could be interested in quantile effects, right? So say conditional distribution function is a regression function. We could be interested in quantile effects, which are nonlinear functionals of the distribution functions. And this poses at least it's a very interesting question, and there are several angles of attack on this, right? Because one could, for example, in the example that I gave, one could still do the bounds on the distribution functions, plot them, and then kind of rotate the axis to get the bounds on quantiles, and then take the Minkowski difference to get the quantile bounds on quantile effects. Or an alternative would be to, if we're in, if the outcome is continuous, we could say, okay, we're really interested in this quantile effect, and we could maybe think that, okay, the confounding is small, and do some kind of Taylor expansion, and maybe obtain some useful bounds in that way. That like kind of, so in other words, like, yeah, the function itself is non-linear, but we could linearize and then use this machinery to bound the linear part and argue that, okay, the nonlinear part is going to be small, so we're going to ignore it, and then we have the bounds obtained in this way. But that's going to rely on this like small confounder effect, which which could give like very practical answers and could be accurate over some domain. But it's not been done, like it's. I think it's a great problem for anyone to work on. Yeah, from my biased personal point of view. Yeah. Thanks.
Okay. Do we have any more questions? You'll need to put your hand up so that the gentleman in the green shirt can see you.
I probably may have missed the part where, let's say you have the latent confounders, all right, but they're sort of orthogonal, right? So in that kind of situation, would your bounds necessarily collapse into a point?
Yeah, that's right, because, okay, so I'm going to repeat the question. Like, what if our confounder is actually not it's a latent variable, but not a real confounder, in the sense that, well, it does not create additional variation gain in the treatment, or maybe doesn't create additional variation gain in Y. Certainly, the expression for bias is going to capture that, because in that case, the covariance is going to disappear. And so that's also captured by this correlation square that I had between the regression error and the Ritz representation error, right? So in the talk, for simplicity, I said I'm going to just set it to 1, like to the upper bound. But in principle, in practice, one could also play with it and say, okay, my observed confounders, they have this, you can actually compute the empirical rho squares, see how adversarial the observed confounders are, and you could say, okay, if my scenario is that the latent confounder is no more adversarial than the observed confounders, then this rho squared is going to also play a role, and this rho squared precisely captures the situation that you have in mind. Yes.
Okay. Do we have any more questions from the audience? Anyone have any more questions? Gentleman over there.
Thank you for the talk. Omitted variable bias is just one of the usual sources of endogeneity. Could this strategy work also for other sources, even all?
Yes.
Thanks.
Yeah, that's a great question. So we briefly mentioned this in the paper. Basically, one example could be a model with instrumental variables. Say there's something called like average treatment effect for compliers or late, like Imbens and Engrist paper. So the late is expressed as a ratio of 2 average causal effects: the average causal effect of instrument on outcome divided by the average causal effect of the instrument on the treatment. If the instrument is itself confounded, then we are in business, because we can use the bounding strategies for the numerator and denominator and obtain the bounds for the IV estimates in that way. So that would be one way to do it for a particular example. There are probably other examples, but this is just kind of the quick answer to your question. But it's a great direction to think about more. Yeah.
Okay. So cognizant of the fact that the next lecture should start in 5 minutes, but I'm just making sure we don't have any last calls. It's like a UK pub, last calls before shutting. Okay, I think the questions have come to a halt. So I'd like to thank you again. This is an absolutely excellent inauguration of the Cox Lecture. And we're delighted you gave us such a great talk, and thank you very much.
Thank you so much.
On behalf of the local organizers, I want to thank you very much that you came. And so this is a little sign of appreciation. I'm sure everybody has already heard this story before, but I always love to tell it. Ruhr University Bochum is the only university in the world that produces its own perfume. We have a scholar in the physiology of smell here on the faculty of, yeah, it's sealed, you have to open, on the faculty of biology. And so he developed this together with a local perfume store. So you can take a smell from Bochum.
Yeah, thank you so much.
Thank you very much.
I am Nina Gantert from the Technical University of Munich, and it is my honor to introduce the next Medaillon lecturer, Remco van der Hofstadt. So Remco studied in Utrecht and got his PhD in 1997 with Frank den Hollander, whom we have heard yesterday, and Richard Gill, who is present as well. And then he moved to McMaster University in Canada as a postdoc, and he returned to Eindhoven as an assistant professor, and then soon moved to Eindhoven, first as an assistant professor, I think, and now he is chair of probability in Eindhoven. Remco is well known for his work on polymers. He started with polymers, but then he moved more towards high-dimensional probability, percolation, random graphs, and discrete probability in general. He has won many recognitions and awards, and I will just name two, namely the David Rollo Prize and his election to the Royal Academy of Sciences of the Netherlands, which was more recent. And Remco is very prolific in discrete probability and has more than 120 excellent research papers, but he has also textbooks, and he has a textbook, a recent 2-volume textbooks on random graphs and complex networks which you probably know, and in case you don't, I recommend it very much. It's a book which is also accessible to students. Remco is very active in the community. He has been one of the applicants for the big network program in the Netherlands, and he has also been for 9 years, I think, director of Urandom. And we are now looking forward to your talk, and before I present you the medal from the IMS.
Thank you very much, Nina, for these very kind words. And it's an honor for me to be giving this medallion lecture here. As Nina was saying, I've been involved in complex networks, mathematical modeling for them, and that's actually a part of the story that I would like to tell today. What I will be talking about today is joint work with two of my very nice and bright colleagues. They're both in the US and they're both Indian from background. The first is Shankar Bamidi, who's in North Carolina, and the second is Shovik Dara, who used to be a PhD student in Eindhoven and is now assistant professor, tenure tracker in Purdue. So my talk will have 3 parts, and I'll start by delineating a little bit what the background is of the type of problems that we're looking at. Complex networks, and models for them, which are called random graphs. So complex networks are all around us. We can think about Facebook, social networks, and so on. And they've actually attracted a lot of attention in the past 25 or so years. And here we see 2 examples, one of yeast protein interaction network and one of the internet, and it's an artistic impression. And these networks come from all sorts of different origins, and you may think that every network from its different background will need a different treatment, a modeling treatment. And to a certain extent that may actually be true, but to a certain extent it also isn't. There are many shared features that many of these networks have, and that's actually what I would like to focus on today, the unexpected commonality between these different networks. And I would like to focus on one of the properties, which is sometimes called the scale-free paradigm. And the scale-free paradigm says that networks, in general, are highly inhomogeneous. And we sort of know that because, even in our scientific landscape, we have people that collaborate with lots of people, but an average person, an average mathematician, if you draw an average mathematician from MathSciNet, for example, which you can do, you will see that this person has not collaborated with many people. In fact, the average person that you draw on MathSciNet is not the kind of mathematician that is sitting here. In fact, it turns out that it's probably a master's student who's collaborated with his or her thesis supervisor on a single paper. So they have very few connections. Whereas, of course, you do have many people who've collaborated with tens or hundreds of people. And that's the kind of inhomogeneity that we're particularly interested in. And here we see 2 examples in a form that you will often see in the applied complex network literature. They're called log-log plots because you plot a log of a proportion versus the log of something, in this case the degree. So the degree is the number of connections that the individuals in the network have. And what you see is, because of the log-log plots, that the bottom of these plots correspond to very few vertices, but these vertices have extremely high degree. That can range up to 10,000, 100,000, or even more. So for example, if you do this for citation networks, there's one very influential paper by Barabasi and Albert, and in citation networks, your degree, particularly your in degree, is the number of citations. And this single paper has 40,000 citations. So you can't really explain that in terms of, let's say, things that are roughly sort of homogeneous in nature. They are highly inhomogeneous, and often the elements in the network that have this very high degree play a very important role in the functionality. So we generally model these networks using random graphs, and we very often model the functionality of these networks using stochastic processes on them. And we've seen beautiful examples yesterday in Frank's talk, where we were talking about opinion dynamics, which is acting as a stochastic process on a network. So you have this double randomness. That's particularly what we see here. Now, in Frank's talk, the networks were either not at all inhomogeneous, think about random regular graphs, or maybe mildly inhomogeneous. I will be focusing on the case where they're actually really very inhomogeneous. And many people in the applied networks community are saying that this actually is the prevalent situation. So if you make the plots such as this, what you see is that in the log-log setting, you almost see a straight line. And a straight line would correspond to a probability mass function that is a power law. So the proportion of observing a vertex with degree k will drop off as k becomes large as a constant divided by a power of k. And it turns out that the power there is very important. I will generally denote that power by tau. And in the empirical literature, very often tau values are being reported, they're being estimated. It's an interesting statistical problem. They're estimated and values are given between 2 and 3. Now, why is this relevant? Well, if you look at a power law probability distribution, then the exponent tau will prescribe how many moments the underlying random variable has. And if you have a tau in between 2 and 3, the random variable that is described by this probability mass function will have finite mean, but infinite variance. And we all know that infinite variance processes are the hallmark of inhomogeneity. So that's the kind of networks that are claimed to be prevalent in the world around us, and that's also the kind of networks that I would like to focus on. And in particular, I would like to study a particular process on it, which is called percolation. So there are many models that model these kind of inhomogeneous networks. Preferential attachment models, configuration models, etc. We've heard a few yesterday. I will be focusing on one very specific model, and this is sometimes called the Poisson random graph. And in this Poisson random graph, the inhomogeneity is moderated by vertex weights. So every vertex in the graph, I will just be assuming that the vertices are labeled 1 up to n, and n will be very large. Every vertex I has a certain weight associated to it, and what you should think about is that the vertices with very high weight are having lots of connections. So the weight is basically a measure of the degree of the graph. And in fact, in this kind of model, the wi is very close to the expected degree of vertex I in the graph. The second thing that is very special about this model is that the edges are independent random variables. So everything is described by independent Bernoulli variables, but the Bernoulli variables don't all have the same occupation probability. So if they would all have the same occupation probability, we would be talking about the Erdős-Rényi random graph, but the Erdős-Rényi random graph is not inhomogeneous. And we would actually like to think about inhomogeneous settings. So in these kind of Poisson random graphs, you're able to moderate the amount of inhomogeneity by basically making the weight distribution very inhomogeneous. And that's what we'll be doing. I would actually like to focus on 2 different settings. So the first setting I will be calling the single edge setting. In that case, there's at most 1 edge between every pair of vertices. And then the edge probability is given by 1 minus e to the power minus wi wj over ln, where ln is the sum of the weights. So it has been chosen in such a way to make sure that the average the total number of edges will grow linearly with the network size. So here we really think about a sparse setting, as we see in the real world. Now, of course, you can think about 1 minus e to the power minus lambda as being the probability that a Poisson random variable takes a value at least 1. Okay? So instead of looking at these edge probabilities, you could also look at the related setting, which we will call the multi-edge setting, where we allow for a Poissonian number of edges between the 2 vertices. Okay, and then actually you can go between one and the other by just saying, you know, if I have the multi-edge setting and I collapse all the multiple edges, if there are any, to a single edge, then you're back to the single edge setting. So you can think of them as living on the same probability space. Now, in most problems, actually there will not be any difference between the multi-edge setting and the single edge setting. The reason is that very often these edge probabilities are going to be very small. You should think of this ln as growing linearly in the number of vertices. The number of vertices is very large. So if the wi times wj is not very large, the edge probabilities will be of the order 1 over n, and therefore extremely small. So you're going to see one edge. For most pairs, you're actually not going to see an edge. For a linear number of pairs of vertices, you are going to see an edge, and it's very rare that you see more than one. But in the inhomogeneous setting, this turns out to be different, and that has a profound effect. That's what I would like to talk about. Now, of course, here I didn't say anything about how to choose the weights. And you should bear in mind that I would like to choose these weights in such a way that my graph is scale-free in the sense that the degree distribution is parallel. I will restrict to one very simple setting where the weights are moderated by a certain distribution function, and I will assume that this distribution function is a Pareto distribution, so it's a heavy tail distribution, a parallel distribution. And you can do that in the following way, by taking 1 minus the distribution function, take the inverse, and stick in j over n, and then let j run from 1 up to n. Okay? These weights have an empirical distribution that is very close to the original distribution function f, and I will take a parallel distribution function f, and in that case, the weights have the shape that I've written there in the second formula. And that will correspond to a scale-free random graph, where the weight distribution obeys a parallel, and because the weight distribution obeys a parallel, actually also the degrees will obey the parallel with exactly the same exponent. So the value tau that we see here in this formula for the weights will actually be the parallel exponent in the resulting inhomogeneous random graph. And as I said, I would like to focus on the setting where this exponent is in between 2 and 3, where the degrees have finite mean, but infinite variance. Highly inhomogeneous. All right, so that was the complex networks and random graphs part. A second thing that was in my title is percolation. And we are going to be doing percolation on these random graphs, but in particular, these random graphs are finite graphs. Now, there's a lot of work on percolation, particularly focusing on infinite lattices, and percolation is one of the simplest models that has a well-established phase transition. So you really see a difference in behavior by changing the parameter of the model. So what is the parameter of the model? Well, think of an infinite graph, such as ZD. It has very many edges, and each of these edges you're going to be keeping with a probability p. So p is the parameter of the model. That's basically the edge retention probability. And you do this independently for all of the different edges. And now you're interested in the connectivity structure of the resulting graph. So if you start on ZD, you start with an infinite connected graph, but now you're removing edges, and now the question is there still going to be an infinite component or not? Well, it turns out that there is a phase transition, and below the phase transition, basically all of the connected components are finite, so they're small, dust, you could say, whereas above the critical value, you see a unique infinite component plus a lot of dust. Okay, so this is a prototypical example of a phase transition where you see some sort of microscopic order emerging as you change the parameter of the model, and it occurs exactly at the critical value PC. Now, this model has attracted enormous attention, particularly on ZD, but also on all sorts of other infinite graphs, and people are very much interested into what happens very close to the critical point, because that's where the most fascinating things occur. So at the critical point, we believe that there is no infinite components, but large components are actually pretty likely. So you see all sorts of fractal behavior, and this really is very cool stuff. However, we're not on an infinite graph. And of course, on a finite graph, you can't expect there to be a proper phase transition. Phase transitions occur in the large graph limit. In in fact, if you do percolation, if you look at the probability of any event on a finite graph, that will be a finite degree polynomial. So it can't have jumps, or it can't have singularities. So the way how you should think about that is that somehow these phase transitions start emerging as you make the graph bigger and bigger. Okay, and in the infinite graph limit, it could be the case that you actually do see a phase transition, but you really have to take the graph to infinity. Now, we're interested in taking the graph to infinity anyway, so that actually means that we will be in a setting where phase transitions will become present. Now, again, we're very much interested in the critical behavior of such finite systems, and it turns out to be difficult to define even what critical behavior is. There is no commonly accepted definition of, okay, you know, take any finite graph, this is how you should define your critical value. Okay? So there's a lot of work. Many special examples have been studied where you can actually identify where the critical behavior occurs, but it's sort of a bit on the ad hoc side, and you really do it for each of the different examples in a different way. Now, of course, if you were to think about a very large torus, then it's very natural to assume that the critical value of the infinite system should be critical. That turns out to be true, and it's provable in some settings. However, what turns out to be the case is that in all of the examples that I've seen, the critical behavior occurs not just for a single value, that's due to the fact that the graph is finite, but it's somehow smeared out over a longer, but reasonably tight, window. So this is called the critical window. And for all of the values of p inside this critical window, the behavior of percolation is very similar. Okay, so all of these values should be thought of as being critical. Somehow the width of the critical window, the fact that it's not a single point, is one-on-one related to the fact that the graph really is finite. Okay, so of course, again, you expect the most interesting behavior to occur for values of p that are close to this critical behavior. Because there, I mean, you're not going to be seeing one giant component that contains a positive proportion of the vertices, but rather sort of fractal-like, smaller size components that are still quite large. Okay? So that's where the interesting stuff happens. And in particular, because we're dealing with highly inhomogeneous graphs, the question is how the inhomogeneity enters into this picture of a scaling window and the critical behavior. That's what we'll be looking at. Now, before doing that, let's first look at what you could call sort of the phase transition 1.0. So that's the question as to in which cases you're going to see a connected component that contains a positive proportion of the vertices. Okay? And that's called the phase transition. It has attracted a lot of attention in the community. So when is there a giant component, and what is its size? And what are the fluctuations of the giant components, et cetera, et cetera. So if you have a finite graph, the largest that your connected component can be is linear in the number of vertices. And this exactly describes when it is linear and when it is sublinear. And in these random graphs, there is a seminal paper by Bollebach, Jansson, and Reardon studying these kind of models where the edge probabilities are, the edge Bernoulli variables are independent, and the probabilities are roughly of the order 1 over n, so the number of edges grows linearly in n. There's a huge paper by Bollebach, Jansson, and Reardon that studies these kind of settings, and they identify precisely when you have a giant component and when not. They investigate distances, et cetera, et cetera. It's a 120-page paper, and this is one a specific example, and the result that we get is that there is a well-defined critical value, which turns out to depend on the asymptotic weight distribution. So remember that my weights were moderated with a certain function, this capital F here, and this capital F appears in the critical value because it turns out that the critical value is related to moments of a random variable that has this distribution function F. Okay? So the critical value turns out to be 1 over nu, where nu is the ratio of the second moment of this weight variable divided by the first moment of the weight variable. And it's 1 over this. So the critical value is the expected weight variable divided by the second moment of this weight variable. Now, if your weight variable has a finite second moment, then this is a positive number, and then above this positive number you're seeing a giant component, and below this positive number you don't. So this really separates the very well-connected phase to the poorly connected phase. Now, I will be interested in the setting where the variance is infinite. So the variance is infinite is actually the same as saying that the second moment is infinite, and then we see that PC is 0. So what does that mean? It basically means that if I have my network, irrespective of what proportion of the edges I keep, be it 1 in 100 or 1 in 1,000, I will always see a giant component. Now, this giant component will, of course, become very small when p is very small, but in the large graph limit, when we take n to infinity, there will always be a positive proportion in this giant component. That's weird. We don't see this on, let's say, infinite lattices that PC is equal to 0, and you have finite average degree. So it's somehow due to the inhomogeneity that you see this phenomenon occurring, and I would like to investigate that more deeply. Okay? But it's sometimes called the robustness of the giant. It basically says, you know, irrespective of how many of the edges you keep, you're still going to have a giant. I will be interested in the critical behavior of these Poisson random graphs. And there's a huge body of work investigating these kind of graphs, including work of some of the people in the audience. The majority of the work actually focuses on the setting where the second moment of the weights is finite, where you have a well-established phase transition, and you can investigate what the component structure is very close to the critical point. And the way how that is often done is by an exploration process. So you basically start exploring the connected components until you've fully explored them, then you go to the next one, etc., etc. This gives you a stochastic process of sort of the number of active vertices that you still have to explore from. And it turns out that in many settings, these stochastic processes of cluster explorations converge in appropriate Squirrel-Hot topologies to some limiting structure, and this limiting structure can then define the critical behavior of the clusters. So very often these clusters behave in an interesting way in the sense that their sizes grow like a positive power of n, but the power is not 1. So when you have sufficiently weak inhomogeneity, the exponent is 2/3, like in the Erdős-Rényi random graph. But when you have more considerable inhomogeneity, it turns out that the exponents are changed. Now, I could talk about this for hours, but I will not, because I've decided to focus on something else. But I still urge you to have a look at the literature here. It really is beautiful. Again, you do see a bit of the inhomogeneity entering, in the sense that if you have sort of pretty strong, but not as strong as in the scale-free setting, inhomogeneity, reading the scaling behavior changes. It's a bit like the difference between sort of random walks converging to Brownian motion versus random walks converging to stable distributions. Okay. So instead, I'll be looking at critical percolation on scale-free random graphs. And as I try to argue, these are relevant in practice, but they're also pretty interesting. So there, the high-degree vertices, which are sometimes called the hubs, they grow very fast. In particular, they grow much faster than square root of n. And that actually means that if you look in the Poisson setting, where you have a Poisson number of edges between two vertices, the number of edges in these Poisson graphs is actually going to be very large. So that's already indicating that there might be a slight difference between the multi-edge setting and the single-edge setting. And that's what we're going to be exploring. So the main questions that I would like to answer in this setting is how one can define the critical value, and how you can really show or at least understand that these are the relevant critical values. Are there any phase transitions? What is occurring here? And I will be presenting two theorems, one dealing with the multi-edge setting, which turns out to be slightly easier than the single edge setting, and one dealing with the single edge setting. And in the single edge setting, we will see some surprises. So let's first look at the multi-edge setting. So first of all, we're going to be seeing fractal scaling. So fractal scaling means that the largest connected components, they're growing with n, like a certain power of n, but the power is not 1. Okay, so they're mesoscopic, as you would expect to be true in general in critical systems. So, first of all, here I'm taking P to be what I call PC of n comma lambda. It has some extra parameter in it, which is indicating sort of how far we are in the critical window. But as it turns out, the main result in the theorem actually does not depend on lambda. So the behavior is the same for every lambda. You could take lambda to be a half, 1/10, or 10 to the power 5. Actually, in terms of the scaling of these clusters, it makes no difference. However, we see weak convergence of the largest connected components. These are these curly C's with the I underneath it. That's the ith largest connected component. Okay? And the first, and the second, and the third, and the fourth, and all of them, they're of the same order of magnitude. Any finite number of them. And if you multiply by an appropriate power of n, and it's a n to the power minus tau minus 2 over tau minus 1, so that indicates that the clusters have size n to the power tau minus 2 over tau minus 1 in this regime. If you multiply by the inverse of that, you get random variables, and these random variables converge in distribution. It's an infinite vector, so you have to think about how the convergence takes place, but all of this has been done nicely. It's a topological matter. This infinite vector converges to some infinite limiting random variable, and this limiting random variable, its distribution depends on the parameter lambda. But they're always non-degenerate. So they're properly random, they're strictly ordered. The first is strictly larger than the second, almost surely is strictly larger than the third, etc., and they're all positive. Okay? So this is what I believe really describes critical behavior. If you look at your largest connected components, after an appropriate rescaling that is not n, you see things that are properly random. This is exactly what you would expect to be true in critical systems. All right. Now, this p actually can be quite small, because if you look at the power of n in the PC of n comma lambda, it is 3 minus tau over tau minus 1, and that can be any value in between 0 and 1. So it could be that you're killing almost all your edges. You're killing a lot of them. So that's the multi-edge setting. And the second theorem describes the single-edge setting. And again, we take a specific value of p. Note that this value of p is actually different from the one in the multi-edge setting. It's actually much larger. So that means that you need to retain many more of the edges in order to start seeing critical behavior. That's already surprising. Because in all of the results that I've described so far, of the critical behavior, the giant, actually it didn't matter whether you were looking at the single-edge setting or the multi-edge setting. Here it matters. The scaling of the critical value changes. We again take a general lambda, and we divide it through by this power of n. And then we look at the size of the largest connected components. Now, the first surprise is that these critical values are different. The second surprise is that the nature of the phase transition is also different. Remember that in the previous theorem, I would get the same scaling behavior whatever lambda I took. That's not the case here. Here, there turns out to be a phase transition in the value of lambda. And the history of this is quite interesting. So with my PhD student at the time, Shovik Dara, we had proved the first result, and then we were looking at the second result, and we were working very hard trying to prove that certain behavior was true for every lambda. And somehow it didn't work. And we were thinking that this was all technical. And then Shankar Bhamidi came and visited us, and he said, yeah, but are you really sure that the behavior is going to be the same for every lambda? I said, oh, wait a second, they could actually be different. That was really sort of setting us up on our path to showing this phase transition. So what is the behavior here? So again, we rescale the largest connected components, in this case by a very weird exponent in terms of tau. It's some quadratic in tau divided by tau minus 1. Weird exponent. And again, what you see is all of the connected components basically have the same size, but they have different random variables corresponding to them. And again, these random variables depend on lambda. That occurs for lambda strictly smaller than the critical value. But then there is a critical value, which we can explicitly compute. It's some number. And above that value, something miraculous happens. Apparently, somehow, all of these clusters, they merge up into one cluster that is, it's not giant because it doesn't have a linear proportion of vertices in it, but it has square root of n vertices in it. Bear in mind, the scaling behavior in the subcritical regime depended in a very sensitive and weird way on tau. For lambda strictly larger than the critical value, there's no tau anymore. It's always square root of n. We don't quite understand why, but this is what happens. So, also, if you rescale the largest connected component by square root of n, it will converge in probability to a limit, and this limit is deterministic. So the randomness is out. So all of the scaling limits in the subcritical regime, they're proper random variables. They're not degenerate. Above the critical value, all of a sudden, you have this tiny giant, as we call it. It is a giant of sorts. Of course, it's much smaller than the giant itself. That would have n vertices. Here it has square root of n vertices. But after rescaling, it is a deterministic value. And also, it's unique. I didn't write that on the slide, but the second largest component really is a lot smaller. So you see a unique tiny giant, as we call it, and then the second largest component is way smaller. Okay? So that's like in a phase transition. As I described, sort of the phase transition 1.0 for these Poisson random graphs, above the phase transition, the size of the giant is roughly a constant times n, and the constant really is a constant, it's not a random variable, and below it's much smaller. So we see something occurring here, but now at the scale square root of n, not at the scale n. So a bit of discussion. So in the box, I've basically summarized the main features of the critical behavior. So in the multi-edge setting, we don't see a phase transition. We take our P's to be a very specific form, whereas in the single-edge setting, we take the P of a slightly different form, slightly different exponent. And in fact, I have them the wrong way around. And in the single-edge setting, we do see a phase transition. Okay? So physicists in the complex networks community have been very much interested in the nature of phase transitions of percolation, Ising models, and so on these random graphs. This was a phase transition that they didn't know about. And in fact, in the literature, the two values of the critical value, which are different, have appeared. And it was not entirely clear from the literature when you should use which. So I strongly believe that you should always use sort of the single edge one in settings where you have single edges, and the multi-edge one in settings where you have multi-edges, more generally than in this particular model. So this gives an explanation for why you see these two different features, and when to use which. So the scalings were predicted by physics community, but they didn't really tell us which of the two to use. But the phase transition was really novel. Now, it's not so strange that this was not detected by physicists, because we were thinking about simulating. I didn't make any pictures, by the way, of the two different settings, and this is why. So if you look at the exponent that we see in the single-edge setting, that's this weird power of tau, you can plot that as a function of tau, and you can compare it to a half. That's this picture. Now, it's maybe difficult to see, but this is sort of a curve that has a unique minimum. And the height at the minimum is about 0.44. So the exponent, the largest jump that the exponent makes from the critical regime to the supercritical regime, where you have the tiny giant, is of the order 0.05. So that's the difference in the exponents of n. So think about how large you should be picking n before you start noticing that you have this difference. That should roughly be 10 to the power 20, probably even more. Now, we can simulate large graphs, but we can't simulate graphs of size 10 to the power 20. So in simulations, there's this nice phase transition, but in simulations, you will not be able to see it. All right. So I would like to say something about the proofs. And I would like to stress again that in the proofs of the two theorems, the behavior of the hubs is very important. So these hubs play an essential role in the functionality of our networks. And for example, if you think about spreading a disease or a rumor, it would be very helpful to either infect a hub or get the news to a hub, because from there it will spread very quickly. Also in this inhomogeneous percolation setting, it will turn out to be the connectivity between the hubs that runs the show. However, there's a significant difference in the multi-edge setting and in the single-edge setting. So what happens in the multi-edge setting? Well, I have a Poisson number of edges between two vertices. And bear in mind, for the hubs, the weights are much larger than square root of n. So actually, the expected number of edges between two hubs is a positive power of n. And now I apply percolation to it. Okay? So that's basically sort of thinning a Poisson variable. But we know very well, if we independently thin a Poisson variable, then we again have a Poisson variable. That actually makes the Poisson setting very nice. So even after percolation on the multi-edge setting, still the number of edges between any pair of vertices will be a Poisson variable. It's just that you have to rescale the parameter by the percolation probability. That's very nice. It's often called Poisson thinning, and it's one of the key techniques in dealing with Poisson processes and so on. That plays a crucial role here. So that's the first setting. Now, in the single-edge setting, that isn't true, because you're sort of collapsing all of these edges into one, and then you do percolation. Okay? That is a much more significant effect. It didn't matter at all how many edges you had. In the end, you're going to have one edge, and you're going to be keeping that with probability p. So that actually means that the probability will become p times the original edge probability. So that has a much more significant effect. And it's also much more difficult to deal with. And that's what actually separates these two regimes. So the multi-edge setting is the easiest to be dealing with, because it still has this Poisson structure. So we can sort of pull all of the tricks that we had for these type of random graphs out of the cupboard, and we can start working on them. The inhomogeneity does make a huge, significant difference, so scalings will become rather different, but still. And here it's very easy to see why we should pick the critical percolation probability the way how we've done it. Because if you look at the number of edges between two hubs, it will be of the order, well, the W corresponding to it times the W corresponding to the other hub divided by ln, which is the sum of weights, which scales like n. So if you look at the power here, it's going to be n to the power 3 minus tau over tau minus 1. Okay? Now, recall how we picked the critical value. It was a constant over this number. So that actually means that if I multiply the two, I get a number that converges. So that actually means that in percolation, if I take two of the largest weight vertices, the number of edges that will be between them is going to be a Poisson random variable with a certain limiting parameter. So it could be 0, but it could also be positive. Okay? That's how you should think of when you interpret the critical value. It really sort of makes the probability after percolation of having a direct edge between the hubs, it makes it non-trivial, strictly in between 0 and 1. Right. So that's the key in the proof of the multi-edge setting. Now, in the single-edge setting, if you take a hub, two hubs, there's only one edge between, and my percolation value vanishes. So all the edges between the hubs will be killed. There's not going to be any edges between the hubs. Still, it's the hub connectivity, the connectivity between the hubs, that is the most relevant thing. But now it's not one hubs, but two hubs. So you call two hubs connected when there exists an occupied two-step path between them, occupied even after percolation. Okay? So the expected number of two hub paths is exactly that number. And if you think about how many of them are going to survive percolation, you should just multiply by the value of p squared, because there's two edges in them. Okay? So as it turns out, you can do this sum in the setting that I've been interested in, and it turns out to have this structure. And what you see is that sort of these rescaled weights, they're going to be converging to some finite functions of I and j. And then there is a power of n. And the power of n is 3 minus tau. And if you look at the bottom formula, you multiply that by p squared, and that should converge. Okay, so you should take p to be, well, n to the power minus 3 minus tau over 2. And that's exactly the critical value that we saw in the single edge setting. So that explains why this is the appropriate critical value. But you should bear in mind, I mean, in the previous setting, the single edge setting, the number of edges, I mean, the edges between different pairs of vertices are still totally independent. Two hop paths are not. They could share edges, but they're very weakly dependent. So that's good. All right. Now, a bit of calculus will tell us that if you look at this p squared times this expected number of two-step paths, that will converge to some limiting function that depends on I and j. And here the little wedge is the minimum, and the v is the maximum. So it's some function of the minimum of I and j and the maximum of I and j. And look at these exponents. These exponents are alpha and 1 minus alpha. Alpha is 1 over tau minus 1. It's some number in between 0 and 1. So in particular, their sum is 1. That actually means that this limiting function as a function of I and j is homogeneous of degree minus 1. And that turns out to be relevant because there's an early paper in 1990, long before we mathematicians started thinking about complex networks, by de Wet and Kesten is one of the giants in percolation theory, who've studied these kind of inhomogeneous percolation models, where the edge probability between a vertex I and a vertex j on Z plus is precisely of this kind. Some function h that is homogeneous of degree minus 1. And they managed to compute that there is a critical value for those, lambda c, and below this lambda c, the limiting graph on Z plus becomes disconnected. And that actually means, in my terminology, that there will be disconnected components containing different hubs, because the i's and the j's are corresponding to the high-degree vertices. That is our critical value. And above lambda c, this limiting percolation problem, inhomogeneous percolation problem, will give a connected graph. So the connected graph will correspond to all the hubs being connected, and that's the setting where the tiny giant occurs. How long do I still have? 10 minutes. 10 minutes, okay. So this is the philosophy. And we really made use of these works by de Wet and Kesten. It's a beautiful paper. Now, in order to investigate the supercritical regime, it turns out to be convenient to use sort of the whole machinery of general inhomogeneous random graphs. Now, we can't quite do that in the setting that I was describing, because the edge probabilities after percolation go to 0 too quickly. And the whole thing is too inhomogeneous. So one of the key tricks in our paper is that that we identify the proper scale of the hubs. So you look at the vertices up to some number n of n that depends on the cluster size, but it will be much smaller than n. And you choose it in such a way that if you look at the percolated graph restricted to these vertices, that's a sparse, inhomogeneous random graph. Right? And it's a bit of calculus to show the scaling of this nn. I will not be doing that, but it's some power of n that again involves this exponent 3 minus tau over 2. And if you look at the collection of vertices with the highest weights of this size, it turns out that all the vertices there have weights that are of the order square root of n. So they're really pretty big. They're really very hub-like. So before percolation, these will have degrees of the order square root of n. Okay? Now, if you look at it, if you then take the critical value and multiply by the edge probability, so this is the edge probabilities after percolation, it turns out that you can write it in a specific form. It's some function of I divided by this n, and j divided by this n, divided by n, the size of the graph. And that's actually precisely the setting that Bollebach, Janssen, and Reardon investigate. And they do this in such a large amount of universality and generality that we can just pull the result out of their paper that will tell us when there is a giant and when there is not. When there is a giant, that will be corresponding to the tiny giant that I've been talking about. And when there is not, it's a subcritical regime. Okay? All right. So, there is a phase transition there, very much alike the one that I described in one of my very first slides, the critical value of Poisson random graphs, so the phase transition 1.0. And in the supercritical regime, and they actually give you ways to compute the critical value explicitly, in the supercritical regime, the giant within this smaller set of hubs will have a size that is of the order the number of vertices in it. But of course, we're now restricting attention to a small subgraph of our original graph. That's actually not the full graph. So we still need to add to that all the connections to sort of lower degree vertices. And as it turns out, the tiny giant, which has size square root of n, is basically the total degree of the giant multiplied by the percolation probability. So after percolation, that corresponds to, you look at this giant in this smaller set, and you look at all of its neighbors in the full space. That's what it is. And if you do a bit of arithmetic, you see that that value is of the order square root of n. That's a bit of calculus. So that explains why you get this phase transition to size square root of n. I didn't do all the arithmetic, but I hope that this is clear. All right. Now, there's a bit of a conundrum that we got stuck on for quite a while. And the conundrum is the following. So here I have a lambda c, right, which comes from the Duret and Kesten line of work, which is an explicit value. Here you also get a critical value, but potentially they could be different. So we actually had to use a little bit of functional analysis in order to show that these two critical values in fact coincide. If they wouldn't, it would have been even weirder. Then there would have been an intermediate phase, which we would not even understand. But this took us some time. All right. I'm at the end of my talk. What are the conclusions? Well, one of the conclusions is that if you do percolation on models for complex networks that are highly inhomogeneous, like the ones we see in the real world, single edge versus multi-edge behave differently. That was rather surprising to us. Even the order of the critical value, PC, as a function of n, it changes. The critical behavior is determined by the connectivity between the hubs. But the connectivity also changes depending on whether you're in a single edge setting or in a multi-edge setting. So in a single edge setting, you have to go with 2 steps between the hubs after percolation, because most of the edges between the hubs will be sort of destroyed. In the single edge setting, apparently, you can still use 1 edge. So that's one-step path versus 2-step paths. And there is a finite critical value in the single edge setting, which is something that we certainly had not expected, and it was quite a surprise. And we've been telling this story to physicists involved in the complex networks domain, and they were very surprised. They immediately started to see whether you could observe these critical values and this difference in critical behavior in simulations, and that turns out to be extremely complicated. We're still not able to do that. Now, percolation is one of the basic models in probability theory, and it's actually used for to study many other phenomena as well. You can think of it as being a model for epidemics. But for example, very recent work has shown that there is an intimate relation between the critical behavior of percolation and the behavior of minimal spanning trees. So in minimal spanning trees, you put IID edge weights, let's say uniforms, on all of the edges, and then you compute the minimal spanning tree with these weights. And the behavior, the critical percolation behavior is intimately tied to the scaling behavior of such minimal spanning trees. Now we see different behavior in terms of the critical behavior in percolation. That should be reflected in a different structure of the minimal spanning trees. I think that's a very fascinating problem. It's probably quite difficult, but I would be very happy to investigate that further. Of course, I've been talking about a very specific random graph model, the Poisson random graph. It's a beautiful model, and it's used a lot, but there's many more models. For example, in a talk yesterday by Frank, we were told about the configuration model. And also in the configuration model, there's this interesting dichotomy between a single edge setting and a multi-edge setting. So in a configuration model, you can have multiple edges, but you could also investigate the erased configuration model, where you basically collapse all of these edges to 1. This work is suggesting that the critical behavior will be different between these 2 models. But that's for the future. For now, I would like to thank you. And here are some references.
Thanks, Remco, for this inspiring lecture. I'm sure there are questions or comments. Frank?
So Remco, there's been a lot of debate about this scale-free paradigm.
Yes.
How would that affect, or would need to affect your results? Is that more going to be showing up in some finite scaling effects, because you take a model and you make an assumption that you have pure thing? So if you would want to bring that in, how would you have to do that?
That's an excellent question. Indeed, there's a lot of debate about whether this scale-free paradigm is correct. For me, it's a modeling paradigm. I mean, it's obvious that we see networks in which the second moment, the empirical second moment, is very large. And if you want to model random variables for which the second moment is large, well, you take power laws. Okay, so you could interpret it in terms of just a modeling paradigm. High amounts of variability will lead to power law distributions. That would be my take on it. But there's a lot of debate about the statistical issues of estimating these exponents in real-world networks, etc., which are very tricky because degrees in networks are not IID random variables, even though people are assuming that. So that's one answer. The second answer is, I do not believe that all of these results will be totally universal. So there's many models of random graphs in which you will have scale-free behavior, for example, preferential attachment models. And I truly believe that the behavior in preferential attachment models, also for the percolation phase transition, will be completely different. I don't believe at all that it will be similar to what we are seeing here. So that basically points to the fact that depending on the precise graph structure, the precise rules for how you get connectivities will matter. And in the configuration model versus the Poisson random graph, the connectivity between hubs is very similar. But in preferential attachment models, it will really be different. We already saw that whether you have a single edge or multiple edges makes a hell of a difference, even in this very simple model. So higher order effects in preferential attachment models are certainly bound to enter into this critical behavior. It could even be that the critical value is different. So you can't expect an enormous amount of universality in this particular regime.
Gesine?
Just go halfway. Thank you very much for a brilliant talk. I just wanted, so the example which you showed in the beginning, I think the yeast worker network is the largest connected component, probably, of the yeast network. So are there implications of your results to the analysis of network data which just come as the largest connected component?
Yeah, I mean, if you do percolation, you're interested in the phase transition, right? And most networks are such that they're either connected, and then, you know, the connected component is everything, or there's a unique giant. So, for example, if you look at MathSciNet data, there's a pretty big connected component between all the mathematicians, which contains, I think, something like 2/3 or maybe even more of the vertices, and all of the rest is dust. So, when you're interested in the percolation phase transition, you're interested in large connected structures. So they will naturally be connected to the giant component. Bear in mind also in my Poisson random graph, before percolation there is a giant and it's not containing everything.
Wondering whether there's some mileage in saying that you might actually only observe square root of n. So even if you think you've got a giant component, it might just be a tiny giant component.
Ah, okay. Yes, that's a very valid point. I'll have to think about that. I mean, for example, in the mathematics setting, so you have MathSciNet and you have a giant connected component. Who would be the other sort of network size squared people? That's the rest of the world, or? So we think of everybody as being sort of a mathematician in Spain who hasn't published, and the part in MathSciNet is just the people who have.
Yeah, I mean, there are many publications which are not a MathSciNet.
That's true.
So
yeah. It's an interesting perspective.
Yeah.
So in my setting, I just assume that the network is there, that it's well connected, because if it wouldn't be well connected, you can't have a percolation phase transition to start with. So that's not so interesting. And then we do percolation on that. That's my perspective. But it's a very valid point. You could have alternative perspectives. Yeah.
Thank you for the talk. You mentioned the differences between, say, configuration model where this would not go to Poisson random graph. Which random graphs would you expect to be close or would feature this property, and why? To be close to...
Yeah, that's an excellent question. So, for those of you who know a bit about random graph theory, I would believe that the random graphs that are close are rank 1 random graphs, where the expected number of edges between two vertices is basically a product of two things. So in the configuration model, it would be the product of the degrees divided by the sum of the degrees. Here, it would be the product of the weights divided by the sum of the weights. And you know, it could have a different interpretation, but that's the kind of structure that you would need. And if you go beyond this, it could be that it's sort of more general than that. I would be rather doubtful. I don't think that if you're in a slightly different setting, for example, if you were to take the sum of the weights, you could. That's a well-defined random graph model. I don't think you have similar behavior as we see here. Because the product is relevant, because if you take the product of the weight of two hubs, it becomes way larger than n. And that's crucial in this setting. If you take the sum, it will still be small O of n. So it really depends on the precise structure.
Thanks.
Yes. Ross.
In the phase where lambda is larger than lambda critical, you
Yes.
said something about this tiny giant.
Yes.
And you mentioned that all the other components are significantly smaller. Now, Bollebech, Riordan, and well, that paper says something about the second component and other components. Do you know how that relates to your model after percolation?
Yeah, that's a good question. Our bounds are not very good.
Okay.
So, but even in general, inhomogeneous random graphs, I mean, you would believe that if there is a giant, then the second largest is probably logarithmic. But that doesn't always have to be.
Right.
So you have to be a bit careful. In fact, in this case, I don't know the precise scaling behavior of the second largest component. We do know that sort of all the hubs, basically up to size roughly square root of n plus n to the power ½ plus a little bit, they're all going to be in the tiny giant. So that means that there's not much hubbish behavior left. And of course, you're going to be bound to be needing some hubs in order to get something big in this setting. But these bounds are not sharp.
Okay, thanks.
It's an interesting question.
Okay, I don't see further questions. Oh, sorry. Yes.
Thanks for a lovely talk. A natural tweak to consider, it seems slightly arbitrary that you have a Poisson number. Poisson is the the distribution of the number of edges between two vertices. What if you had some other distribution?
Oh.
Like, I don't know, geometric?
I don't know.
Geometric or binomial? Binomial has the thinning property that you mentioned.
It's a good question. I mean, the Poisson nature comes from the fact that we take our edge probabilities to be 1 minus e to the power minus x, where x is the product. That's important, because that's to leading order x when x is very small. So that's related to this rank 1 setting. It's to leading order of product structure. Of course, for the hubs, that's no longer the case, and there somehow the precise way how the p gets close to 1 when the product becomes very large matters. But other random variables people haven't really considered. So going away from the Poisson and turning it into geometric or something like that, I have not seen so far. Interesting.
Thanks.
I suggest that we delay further questions to the coffee break and thank Renko again.
You have already heard the story about knowledge before,
but I'm still very curious to smell it.
Thank you very much for coming all the way from Eindhoven. I think you are the one of the plenary speakers who had the shortest travel to come here.
Yes,
so
absolutely.
Thanks, I appreciate it very much that you came.
Thank you.
don't take. Yeah. There's a funny story to this. I'll tell you after.
Okay. But just about mine?
About yours, yeah.
I'm sure I know. It has to do with the accents and the sequence.
We'll serve it at the end. Push the start on time. Okay, we'll start right now. So welcome everybody to the Shram lecture. This is the last academic session of the World Congress. Oded Shram was an extraordinary mathematician. His work had a profound impact on probability. He transformed understanding of planar processes from statistical physics to SLE, tying probability theory to complex analysis in a novel way. Oded Shram's life was cut short in a tragic hiking accident in September 2008. The IMS and the Bernoulli Society then jointly instituted a lecture in probability and stochastic processes named in the honor of Oded Shram. The first Shram lecture was delivered at the Stochastic and Processes and Applications in Boulder in Colorado 2013. Patricia Gonzalez will give the lecture today. She got her PhD in 2007 under Claudio Landum. She was the recipient of the Simons Foundation grant in 2014, the ERC grant in 2016, and was an invited speaker at the International Congress of Mathematicians in 2022. She currently serves as the chief editor of Electronic Communications and Probability. Patricia has a very strong publishing record in the field of interacting particle systems, with focus on large deviations, high dynamic limits, and fluctuations. Her key contributions include derivations of the stochastic Burgess equations and the KPZ equation via many interacting particle systems. More recently, she has focused her work on derivation of non-equilibrium fluctuations and correlations of several symmetric models. It's my great pleasure to introduce her as this year's awardee of the Shram Lecture.
Thanks. Thank you. I think he's not on. Ah, yes. All right. Thank you very much. Thank you very much, Siva, for this very kind introduction. So this is the last talk of this very nice event, and I'm very glad that all of you, the ones that are here, made to my talk. So I'm going to talk about hydrodynamic limits, fluctuations, and universality for exclusion processes. This is a long title, but I hope that at the end of the day, there is some nice take-home message that you take with you. And I decided to divide my talk in two different parts. So the first part, I will just review some work that has been done related to hydrodynamic limits and fluctuations for the exclusion process with one type of particle. So just one, I don't distinguish particles. And the second part, I will review hydrodynamic limits and explain some new results that we have obtained last year about fluctuations for systems with more than one conservation law. So exclusion with two particles. All right, so before we start, let me just give what is this physical motivation for studying these problems. So imagine that you want to understand or to analyze the evolution of a gas. The number of molecules is too large, so we cannot and we don't want to give any precise description of the microscopic state of the system. And according to Boltzmann, what we should do is first to find invariant states of the system and then characterize them by some quantity of interest that I call here, I denote it by rho. So imagine that you have our gas. So in the picture there you see on the left-hand side, you have your gas, your particles. Then you fix some, let's say you have the gas confined to a volume, which I represent by the square. And then you fix a point, I call it Q. Okay, maybe here one can see. It's this point here. I fix a neighborhood that I call lambda q, which is very big from the microscopic point of view. And due to the interaction between molecules, you assume the system to be close to let's say, in a local equilibrium, not globally, but locally. And then this local equilibrium, if we have done what we were supposed to do, this local equilibrium is characterized by this function that I call rho, but now depends on the point q. Now you let time run, you ask the same question, and now at time t, which we fix, we ask exactly the same question. So the system now is close to some local equilibrium, which depends on rho at time t and q. And if we assume that this rho is sufficiently smooth, we want to understand what is the space-time evolution of this function. So how do we approach this mathematically? So we discretize our space that I called a lambda, and in this talk, the lambda will always be the space 0, 1, the one-dimensional interval, or the torus. We discretize it according to a parameter n, so in my talk, n will always be a scaling parameter, and as I mentioned, we are going to study or analyze two different types of scaling limits, hydrodynamics and fluctuations. And by doing this, we have a space which I call lambda n, which is the discrete space where particles will evolve. So we will have two scales for space, a continuous one, which is a lambda, and the discrete one, lambda n. And if we want to see a non-trivial evolution, we will have to speed up the time. So again, we will have two scales for time, a microscopic time, which I always be of the form t times theta n, a function of n, and the macroscopic time t. And at each point of this discrete set of lambda n, we will put a certain number of particles. The dynamics will conserve one or more quantities of interest. And this collection of particles, this collection of, let's say, random walks which interact, they are a particle system, and they're in fact a continuous time Markov process. And interacting particle systems, they have been introduced, okay, by Frank Spitzer that you see there on the right. And the main question that we want to understand is the following. What are the macroscopic laws which describe the space-time evolution of the conserved quantities of the system? Okay, so now let's look at a very classical model, which is called the exclusion process. So as I mentioned before, we have two scales for space, two scales for time. Particles wait some time, which is random, and it is given according to some independent Poisson clocks. There will be a transition probability that here in my talk, in the beginning, will be quite general, so I just call it P, but will only depend on the size of the jump. Eta t of x will always denote the number of particles at position x, and in this case, since we are looking at a very specific exclusion process, this eta of x will be either 0 or 1. When it's 0, it means there is no particle at x. When it's 1, it means there is a particle. And so the dynamics is like this. At every pair of sites, x and y, there are Poisson processes, all of them independent. And whenever you see these blue lines here, it means that we see a mark of a Poisson process. And at that position, so you have the Poisson process attached to x and y, particles swap positions. But since we don't distinguish them, we say that, well, nothing happens. It's like the jump is not allowed. But if there is a particle in one position and no particle at the other one, they swap positions, and this particle jumps according to this rate p of 2. Being 2 is just the distance between this point x and x plus 2. As you see in this case, but this is a special case, then we will change it a little bit. The dynamics is just moving particles in the discrete space, so there is no creation or annihilation. So whenever we start with a configuration with a fixed number of particles, the number of particles is conserved by the dynamics. Okay? So this is the quantity of interest, the density. So how do we prove hydrodynamic limits for exclusion process? The idea is to do the following. So we have one conserved quantity. We associate to this quantity the empirical measure that you can see over here. So this is a random measure. I fixed initial configuration eta. Eta t of x, as I mentioned before, gives weight, so it's just 0 or 1. So every time there is a particle at position x, this measure gives weight 1 over n, and then we just sum over the Dirac measures, which are, let's say, supported on the point x over n, which is the macroscopic point, the point in the macroscopic space corresponding to x. And I take a time scale t times theta n. So this is my object. I want to understand where this measure is converging and in which sense. And the assumption is the following. So we start the system. We assume that eta of 0 is distributed according to some probability measures that I call mu n, in which we usually say that they are associated to g. So what does it mean? I fix a function g, which is defined on this macroscopic space lambda and takes values in 0, 1, which is measurable. And then we assume that, so this is an assumption over the initial measures μn, is that this limit is true. So what is this limit? So on the left-hand side is just the integral of a function h continuous with respect to the empirical measure at time 0. And we assume that this random measure is converging in the weak sense to a deterministic measure, which has a density with respect to the Lebesgue measure given by this function g. And the goal is to show, of course, that, OK, still I have to say in which sense this is true, because this is random. So we say that this is true in probability with respect to μn. And this is our assumption on the initial measures. And then what we want is to show that if this is true at any time, if this is true at time 0, then it is true at any time t, but then the limiting measure, it's again absolutely continuous with respect to the Lebesgue measure, deterministic, and this function here is a solution, in some sense, to some PDE, which coins the name hydrodynamic equation. And there are several methods to prove the hydrodynamic limit. So here on the right side, you can see the entropy method, which was developed by Varadan and collaborators, the relative entropy method introduced by Yao, and propagation of chaos, also very well developed by Enrico Presute and Anna Damasi. All right, so examples of hydrodynamic equations that have been derived for the exclusion process so far. So here I just put some examples of them, but I just wanted to fix, for example, the first 3 ones, because they will be important in what follows. OK, in the meantime, I will run here some simulations so that you can see the random system in black. So now I allow more particles per site, and in red, we have a solution of some PDE, which is the heat equation in this case. So there are, in the first 3 cases, there are 3 equations that we can get, and these the 3 cases, what we are thinking about is just symmetric exclusion, first case. So particles go to left and right with rate 1/2, let's say, or 1. And we have to speed up the time in diffusive time scale, and the hydrodynamic limit that we get is given by the heat equation. Now, if we take a P, a transition probability, which is weakly asymmetric, so let's say particles jump to the right with rate 1 + 1/n, what we get is a little bit of contribution from the asymmetry, so you have a viscous Burger's equation. There is this new term here in the equation, again in diffusive time scale. But if the system is asymmetric, so if the rate to go to the right is p and to go to the left is q, what we get in hyperbolic scaling, so we don't need to wait so long because we already have a preferred direction, so things change faster, what we get is the inviscid Burger's equation given by this. OK, then we can also get porous medium that you see below. In that case, we can take an exclusion process for which the rate, you have to require a certain number of particles close to where the jump occurs in order to have this Laplacian with rho to some power m that you can see here. I hope you can see it in diffusive time scale. And you can get fractional versions of these equations by allowing particles to give long jumps according to some probability that I wrote here. And the role of this P is that, OK, this is a choice. We take a P, which is a transition probability depending on the size of the jump that decays like this. And for gamma bigger than 1/2, in fact, the system gives long jumps. So in the exclusion process, particles give long jumps. But since this P has finite variance, what we recover is not the fractional versions, but the diffusive version. So you replace the fractional Laplacian operator by the Laplacian operator. But when gamma is between 0 and 2, we get fractional equations. OK, so now, I never mentioned anything about boundary conditions, but of course that we can add boundary conditions. And here I'm just putting 2, let's say, different examples. So I'm allowing, again, the exclusion process with just one particle per site. And in the first drawing that you see above, I'm adding a barrier. What do I mean by this? That every time a particle wants to jump from a position from z minus to z plus, the rate p that you see here, it is being multiplied by a factor of n. So let's say alpha divided by n to the beta. And this means that if I increase beta, if beta is positive and I increase it, it means that microscopically I'm slowing down the rates to go from z minus to z plus. Everywhere particles jump, if particles jump on the left side here, nothing is affected. The rate is just given by p, and also here. So the question is, I have this barrier at the microscopic level. What is its influence when we go to the macroscopic limits? Do I see any kind of boundary condition? And how do I see these boundary conditions depending on the value of beta and alpha? Now this P again, so I'm not mentioning because it's exactly the same P that I defined in the previous slide. And as I mentioned before, when it has, let's say, when gamma is bigger than 2, it has a finite variance. So what you recover is that you have two different, let's say, the nature of the PDEs that you get are different. And I will explain quickly what kind of zoos of equations one can get for the second model. So the second model here that you see down, so I distinguish particles with two colors, but it's just to make it easier to understand. So here, from the, let's suppose that this is the point 1, 2, etc., n minus 1. So I call to this set the bulk of the system. And my particle system is just looking at these gray particles. And these blue particles are just representing reservoirs. So here I didn't draw everything, but imagine that at every point in Z minus, you have a reservoir which is injecting and removing particles in the system according to this transition probability P. But now, okay, and the same thing on the right, every point here from N on, I add a reservoir which is also injecting and removing. But you see that on the left side, I have some parameters here, alpha and gamma, and on the right side, I have beta and delta. And these reservoirs, they try to tune the intensity, let's say, the density. They try to somehow fix the density of the reservoirs. Moreover, I'm putting here, I'm slowing or fasting down the boundary dynamics by multiplying these rates that you can see here with a factor n to the minus theta. So if theta is negative, it means that the boundary dynamics is quite fast, while if theta is positive, I'm slowing down the dynamics. And the question again is, what happens at the macroscopic level when I have these rates? What kind of PDEs do I get, and what kind of boundary conditions? So the next slide, I will explain to you. So just try to fix the second case where you have this bunch of reservoirs. The nature of the PDE depends on the value of this gamma that you see here on the definition of the transition probability, and it's like this. When gamma is greater than 2, greater or equal to 2, we will have reaction diffusion equations. Okay, in fact, there will only be one case, but let's say the nature of the PDE is this, but depending on the value of theta, we can get just the heat equation, just the reaction term, or both. Now, when gamma is less than 2, what we replace is this Laplacian operator by an operator which is somehow a fractional Laplacian. But since here our domain is just the interval 0, 1, this is what is called, so this operator L here that you see over there, is called the regional fractional Laplacian, which is given by this. So this is the same definition of the fractional Laplacian, but now you integrate in 0, 1, in the macroscopic domain that we are looking at. And these functions here that you see, these V0 and V1, they appear when the intensity of the reservoirs is strong. Okay? So in the next slide, I will explain what kind of PDEs we get for the second model, for the model which is down. And before I forget, I have to say that this has been developed with Cédric Bernardin, who is now in Moscow University, and with some of our students, because these models, whenever you try to change a little bit the rates, they start to be very, very rich. You will see now. So this is a plot of the type of equations that we can get, and I will explain it quickly. On the horizontal axis, what you see is the value of gamma. So from this point on, gamma is greater than 2. This is exactly the line gamma equal to 2, gamma equal to 1, and gamma equal to 0. The vertical line, so from here down, is the value of theta being negative, while from here up is theta being positive. So I just explained what's going on this right side, because then, as I told you, we just replaced the Laplacian operator by the fractional Laplacian, the regional one, and then the boundary conditions, we replace them by their fractional versions. So here on the right side, you see that when gamma is bigger than 2, and theta is between this line here and this line here corresponds to theta equal to 1, what we get is Dirichlet boundary condition. So this means that the reservoirs are strong, and they actually fix the value of this function rho as being some fixed value at the boundary. Now, when we look at theta in this case here, this is the case, in this line here that I hope you can see, this is the case where the two dynamics, the bulk and the boundary dynamics, they have exactly the same strength. So what we get in this line here is exactly this equation. again, with Dirichlet conditions. Now, everywhere here, this is the case when theta is negative, which means that the reservoirs, they are very, very strong. And so we only see a reaction equation with Dirichlet conditions. And now when we go up here, so it means that we are really slow in the reservoirs, this line here is for theta equal to 1, which means that there is a balance between the boundary dynamics and the bulk dynamics, and what we get is the heat equation, but with Robin boundary conditions, and below theta, let's say above theta bigger than 1, what we get is Neumann boundary conditions. So this can be quite rich, and once you go to the left side, let's say to the part gamma between 0 and 2, you replace this heat equation with this fractional version that I mentioned before, this equation over there, given in terms of this regional fractional Laplacian. All right. So second thing, so this is one type of scaling limit that one can get. The second one has to do with the fluctuations around this typical behavior. So imagine now that we start our system, for example, from a constant profile, that I put here as, let's say, call it rho, and we are trying to look at all these, let's say, we can see it here in the simulations, we can try to look at all these fluctuations of the random system in turn of this constant profile. So how we characterize these fluctuations? So I'm going to stick now still to the exclusion process with just one type of particle, and I will distinguish what happens just in the case of, by now you can forget the long jumps case, just the nearest neighbor case. So let's see. First, where do I start? What is my starting measure? In hydrodynamic limits, I told you that we had to start from measures which are associated to a profile, and this is quite general. So here I just assume that hydrodynamics is true as long as this assumption is valid. But now when I want to go to fluctuations, this is very hard to do it very generically, I mean out of equilibrium. So let us suppose by now that the exclusion process starts from its invariant measure. And in the case here, so just think about jumps to nearest neighbors, the invariant measures are Bernoulli product measures. This means that the variables eta x and eta y, they are independent. And eta x has Bernoulli distribution with parameter rho. When we put the system with boundaries, things are more complicated. In the long jump case, it's especially much more complicated. And what we do, so how we analyze these fluctuations, is to look at what is called the density fluctuation field. So what is this? OK, you have a formula over there. But this is just, you take a function h, which has certain regularity. You integrate it with respect to the empirical measure. So this is what I represent by this bracket here. But since this empirical measure is just the sum of Dirac measures, what we get is exactly this term here divided by n. We remove the average of that quantity with respect to the invariant measure, with respect to the Bernoulli measure, and we multiply by square root of n in order to be in the CLT scaling. Now, what we want to understand, so now just fix these dynamics here. So particles are just moving to left or right with rate p and q. And what we want to understand is in which sense this linear continuous functional converges, in some sense, to a process yt, which is a solution to some SPD, and which has SPD is that. OK, so now there are three cases that I want to distinguish. In the case where we have, let's say, so nearest neighbor, symmetric rates, so I'm putting here p equal to q, or if we want to consider the weakly asymmetric case in which p is equal to 1 plus a little bit, let's say, e divided by n to the gamma, and gamma bigger than a half, what we get is the Ornstein-Uhlenbeck process. So yt is solution to this equation. In the asymmetric case, and in hyperbolic scaling, the same scaling that we have the hydrodynamic limit, what we get is this process solution to this equation. And p is different from q. And you see here, when you look at this equation, that if I choose rho, the parameter of my Bernoulli measure, as being equal to a half, what we are getting is that dyt is equal to 0. So this means that for the precise value, when the Bernoulli measure is being taken with rho equal to a half, in the hyperbolic scaling, I do not see any evolution. So we need to go to a longer time scale. OK, to summarize, if you take the WASEP, which is in fact the case that I want to understand and to explain today, so if you take weakly asymmetric rates, but now you make this precise choice, gamma equal to a half, because gamma bigger than a half, we know that the system is, there is a weak asymmetry, but it's not strong. So basically, when you take gamma bigger than a half, you get exactly the same thing as if the system were purely symmetric. But now when you take gamma equal to a half and rho equal to a half, what you get is this equation here, which is called the stochastic Burger's equation, which has already been mentioned in this talk, in in this conference this week. And you see that the difference between this equation here and the one that you get for the symmetric case is that here there is this nonlinear term, and it appears because the intensity of the asymmetry now, which is being taken now as E divided by the square root of n, is exactly as the same strength as the symmetric part. And so we have this solution to this equation, which I'm not going to tell you now what it is and what do I mean by a solution to this equation, but it will appear in the next slides when we will discuss the case where we have two conservation laws. So there is a picture here down in the slide that you can see. So on the horizontal axis, you see the value of gamma. On the vertical one, you see the value of the time scale that I call n to the a. So in diffusive time scale, when a is equal to 2 and gamma is bigger than 1/2, what we get is this process here that I represent in purple, the Ornstein-Uhlenbeck process. When gamma is equal to 1/2, it's the stochastic Burger's equation. And below here, what we should get is what is called the KPZ fixed point, which is the process that has been obtained in the case where you look at this asymmetric simple exclusion in the n to the 3/2 time scale. So you already see here, when we have one conservation law, that there is a transition, there is a way to go from one universality class, which is the Edwards-Wilkinson, which means Gaussian fluctuations or Ornstein-Uhlenbeck processes in the limit. And when we change the value of gamma, let's say, of the asymmetry in the rates, which are here, you go to the stochastic Burger's equation, and then one should get to this KPZ fixed point, let's say, to the KPZ universality class. All right, so let me tell you that, well, you see there on the slide, I have been developing these techniques to derive the stochastic Burger's equation or the companion equation, the KPZ equation, from several interacting particle systems. And in a couple of slides, I will tell you in which way we say what is a solution to this equation and how we interpret this nonlinear term. And this has been derived with Milton Hara from IMPA since many, many years ago, more than 10 years ago. All right, so now I hope it's clear. If you have any question, please interrupt me. What happens if we have more than one conservation law? So now suppose that our process doesn't have any type of boundaries. We just look again at nearest neighbor rates and the weakly asymmetric case, because somehow what I want to explain to you today is how to, let's say, to obtain this type of transitions of crossovers between one equation to the other, let's say from one universality class to something which goes on the way, which is a stochastic Burger's equation, from a much, much richer model than just a model with one type of particle. So that's what I want to discuss. So let's suppose now that instead of having just one type of particle, or you can think that we have two types, let's say particles and holes, but now we have two types, or three types, let's say A, B, and C. So now I'm on the torus. My discrete space is just the torus with endpoints. The macroscopic space is the continuous torus. I'm taking weakly asymmetric rates given by these, which I hope you can see. So I'm fixing three quantities that I call EA, EB, and EC. And this will tell me, these constants will be defining the rates at which particles with different types exchange. And so you can see down there what we are defining. So particles, let's say, A exchanges with B in this direction with this rate 1 plus EA minus EB divided by 2n gamma. So there is a symmetric part, which is this part with 1, which will give rise in the SPD to the Laplacian term. And there is this weakly asymmetric term here, which depends on this EA and EB. And we do the same definition for all the other particles which are involved in these rates, in these jumps. Let's say B exchanges with C, exactly with the same rate, but you replace EA by EB and EB by EC. Is it clear? So this is the definition of the exchange rates between particles with different types. So what we want to understand is two things. First, hydrodynamic limits. How do they depend on these constants? Are we going to get a system of uncoupled or coupled equations? And fluctuations. So first thing to realize now, we are on the torus. As I mentioned before, the number of particles, it's fixed, it's conserved, and the number of each type is also fixed because particles are not created or destroyed as happened in the case with boundaries. Here, there is not this boundary dynamics. It's just an exchange dynamics. They just go along the torus, changing with each other. And we look at evolution in diffusive timescale. Okay? And now we do the following. First, hydrodynamic limits. So before I told you that when we had one type of particle, eta of x was telling me if I had a particle or not at the position x. So it was either 0 or 1. In this case, eta of x is giving me which type of particle I see at position x. So eta x can take the value alpha, and I'm assuming that alpha can be equal to A, B, or C. Okay? Psi alpha of x will tell me if I have a particle, so it will be equal to 1, if I have a particle of type alpha at position x, or 0 otherwise. Is it clear? I associate to each one of these quantities the respective empirical measure. So for each type, for each alpha, I define the empirical measure in this way. So I look at this psi alpha of x, which is either 0 or 1. If there is a particle of type alpha at x, I give weight 1 over n, and I just take the sum of Dirac measures. Now, as before, we take a measurable profile that I call G. So in fact, I have 3 profiles, G, A, G, B, and GC. And don't forget that since we are on the torus, I can recover the particles of type C by looking at the particles of type A and B. So in what follows, in all my results, now you will only see results for particles of type A and B. Now, we assume, as we did before, that these initial measures, mu n, so the initial distribution of the system, it is associated to a profile, to the profile G alpha. So this means that this is true, and this is exactly the same result, the same, let's say, assumption that we had before, so I'm trying to go there. It's exactly the same assumption that we have here for one type. Now we have this assumption for each type of particle. So let me go back. And given this assumption, we can show that, in fact, the empirical measure for each type is converging. And the density is given. In fact, we have 2 densities, rho A and rho B, and they solve this system of coupled equations in the case where gamma is equal to 1. So you see here that these equations are coupled because this term here is giving us the gradient, and you see here in this matrix products with rho A and rho B. Okay? Now the question is, okay, we have hydrodynamic limits. What do we know about fluctuations? How can we cook up some SPDs for each type of particle or for some collection, some other quantity? And now we say the following. So when you look at fluctuations for one type of particle or for systems with one conservation law, what we do was simple. We just defined the density fluctuation field as the empirical measure associated to that quantity. But now, when we have more quantities, and you know that any linear combination of conserved quantities is again conserved, maybe we have other options to define these density fields. Okay, even worse is that you might have systems, which is not the case here in my talk, but you can have systems in which each conserved quantity lives in different time scales. So maybe one lives in diffusive time scale, maybe another one lives in a time scale which is, for example, hyperbolic. And these conserved quantities, they might correlate. So about a decade ago, in 2014, Herbert Spohn, Gunther Schutz, and many other collaborators, they developed what is called the nonlinear fluctuating hydrodynamics, or also called mode coupling theory, which tells us which kind of quantities we should obtain, we should consider, and what kind of predictions. And here on the right side of my slide, you see some of the examples that have been predicted. So for example, you see, as we have seen already before here, the transition between these Edwards-Wilkinson, these Ornstein-Uhlenbeck limits to the stochastic Burgers or the KPZ equation and the KPZ fixed point. But many others have been predicted, like, for example, these Ornstein-Uhlenbeck processes, but when you replace these operators, let's say the Laplacian operator by fractional Laplacian operators, so we have this Levy 5/3 or the Levy 3/2 or Golden-Levy, a much more richer scenario that you expect when you have more than one conservation law. The question is how to obtain these limits. Okay, so every time we try to prove something, I mean, how to derive these PDEs or SPDEs from particle systems, let's say, that's why I say over there that the major difficulty that we face is how to close the equations, how to rewrite, let's say, a closed equation for your quantity. And I will explain you what happens in this model because it's simple but still complicated. So I hope it will be clear. But before that, how does nonlinear fluctuating hydrodynamics predicts these limits? So the starting quantity, so let me try to go back, just to recall that our model is this one in this specific talk. The generator, as I mentioned before, is given by this, and you exchange particles according to these rates that you see here. And the starting point is to look at what is called the current. So when you apply the generator Ln to psi alpha of x, which is telling me if I have a particle of type alpha at position x, I get a gradient, and this gradient is a gradient for particles of type alpha that I call J alpha of x, What is it? It's the instantaneous current, so it means it is the difference between the jump rate from x to x plus 1 and from x plus 1 to x of particles of type A. Okay, there is a huge formula, but what I want you to retain in this formula is two types of terms. The term that you see here, it's basically, it's a new gradient. So think that when you apply the L to psi x, you already have a gradient here, which will allow you to make some summation by parts, and then you have another gradient. So somehow you're going to get some discrete Laplacian out of this term, which will give the diffusive term in the equation. All right, that we forget this case now. But in this last part here that you see on the right, there are terms of, let's say, quadratic terms, let's say terms which are products of the form psi A, psi B, or psi A, psi A, or psi B, psi B, and terms of degree 1 in psi A, right? You can see that there are two terms over there which are of degree 1. For the particles of type B, you can compute exactly the same formula, and it's very similar. So JB is exactly the same, but we exchange A with B. Now, for this model, the stationary measure is still product, so it's given by this. I look at the configuration, I look at eta at position x. If it's equal to alpha, I give it the weight rho alpha. And now I'm going to choose a particular choice of the rates just to make it easier. So I choose the case in which the constants EA, EB, and EC, they satisfy this identity in red here. So this means that EA is equal to EB, and EA minus EB is equal to E, a constant. Now, what we have to do? We compute the expectation of these currents with respect to the stationary measure. Okay, we obtain these two quantities. We compute the Jacobian matrix, and just to simplify the presentation, I'm choosing rho A equal to rho B equal to a third, and we get this. And now we try to diagonalize this matrix, and we find out that it has eigenvectors and eigenvalues. So the eigenvalues, I call them V plus and V minus, which are equal to this, and I will comment a bit on this expression here later. And the eigenvectors are given by tau plus and tau minus. And so when you apply to this matrix R, when you apply the matrix to the quantities that we start from, we get new quantities that I call phi x plus and phi x minus, which are just given. So you can see here that phi plus is just the difference between psi A and psi B, and phi minus is the sum. So basically what we are doing is to change coordinates in our system. And so what mode coupling is telling us is that you should look now, instead of looking at the fields of particles of type A and type B isolated, you should take this proper linear combination, which here is just the sum or the difference, and you should look at them in some frame. What does it mean that? It means that in my density field, I will replace the function f, and I'm taking the particles as if they were traveling with a certain velocity. Which velocity is this? Is the velocity given by the eigenvalues of the matrix J. Okay, up to here, what mode coupling or nonlinear fluctuating hydrodynamics is telling us is what are the quantities that we should look at. So these are the quantities, these are the velocities, but what are the limits? How do I predict the limits? And these predictions, they are based on what is called coupling matrices, and I will explain to you what they mean. So in this particular case, and this is really particular here for this model, the coupling matrices can be computed. Okay, there is a formula that you can see there, and in this specific case, there is a 0 here and there is a 0 over there. I hope you can see them. This means that we can only get two types of limits. It's either KPZ or Edwards-Wilkinson. And when I say KPZ here in mode coupling, I'm talking really about this KPZ fixed point, for which we don't have results. So these predictions are always being done in the case where when we go back to the graph, I'm looking at this plot here, I'm just looking at the case gamma equal to 0. So whenever I talk about KPZ in my talk, I'm talking about stochastic Burger's equation. And they say the following: you can only get these pairs. Either you have one field which is KPZ and the other one which is Edwards-Wilkinson, both Edwards-Wilkinson or both KPZ. And one of the claims is that these diagonal terms are important, these ones, but the off-diagonal terms, they are completely irrelevant to the limit. So what does it mean, these diagonal terms? What are these entries of these coupling matrices? It means the following. If I am looking at evolution, for example, of phi plus, I'm taking the time evolution of this quantity, and you see that before, here in the current, I had products of these terms. I have quadratic terms. So basically, the coefficients of these matrices are telling me which kind of coefficients I see in quadratic terms, for the new quantities. So for example, G plus, I'm having here a 0. This means that in the evolution for phi plus, I do not see any term of the form phi minus squared. because I have a coefficient 0 here. When I look here at this one, this means that I have a 0 here, so I don't see a phi plus squared in the evolution of phi minus. And because of that, that's the reason why we have these limits. Of course, that I will not explain why this is, I mean, there are other assumptions which are done, but what I want to tell you is that with colleagues, and for this model, we prove that these off-diagonal terms, in fact, which are claimed to be relevant for the limit, it's in fact true. So let's see how we do this. So I think my time is almost gone, or maybe close to be gone. No? 5 minutes, okay, I try to be fast. Okay, so let me tell you, there are 4 cases to distinguish. Either all these constants, 2 of them are equal, or all of them are different, and also another important thing is that, okay, how we obtain the limits, who is we? So this is a work with Giuseppe Cannizzaro, Riccardo Misturini, and Alessandro Ocelli, and I will present to you how we obtain these limits just in the first case, which is the case that we discussed before. So the new quantities that we are looking at is just the difference between particles of type A and B, the difference, the sum, and with these 2 velocities. I said that I would say something about the velocities. Here in this model, and you can see here on the slide that all the velocities are of the form V plus is -1 times V minus. But this is a coincidence for the model. This is not important. The only thing which is important for the results to go through is that the velocities are different. Okay? That's what is important. That's why I say over there, the new fields, they have different velocities. So they are living in the same time scale, but they are just, when time goes, they are really, really getting apart. Okay, the theorem is this. Whatever is the case, I distinguish here just, okay, I'm going to distinguish the whole cases, but whatever is the case, if gamma is bigger than 1/2, these new fields, Z plus and Z minus, Zn plus and Zn minus, they converge for the case gamma bigger than 1/2, so don't forget gamma is the, let's say, the strength of the asymmetry, so I'll try to show you where is the rates, which are here. So when gamma is bigger than 1/2, we have exactly the same as we had for the 1 particle case, and what we get is just Ornstein-Uhlenbeck. So I mean that these parameters here, lambda plus, lambda minus, and m plus, that you see here in this equation, this is 0. So you only get the diffusion term and the noise. So Ornstein-Uhlenbeck as before. Now, when gamma is equal to 1/2, bizarre things can happen. And, okay, let me start with this case here. Lambda plus, so when we're looking at the limit of Z plus, the quantity which is the difference of the 2 quantities, psi A minus psi B, lambda plus is 0, which means that there is non-linearity, so I'm not expecting to see any stochastic Burger's equation. But there is a drift term here, m plus, which appears in this equation. And this term here is a consequence, so this is one of the consequences of the fact that we have this product, let's say these mixed terms. Now, on the third case here, it's a bit more complicated because this is the case where the 2 quantities, both of them, they have this parameter lambda plus and lambda minus, which is different from 0. And so you get 2 stochastic Burger's equations, okay, in this case. So what do I mean by a definition? What is the definition of an energy solution to the stochastic Burger's equation? And this definition is exactly the same for the 1 particle case. So suppose you have that equation which is written over here. We say that we have a stationary energy solution if Zt is a white noise with a certain variance. It satisfies an energy estimate which justifies the fact that you have here this square, this product. So this is a singular SPDE, as we have seen this week in the talk of Hongfeng Sun. You have this nonlinear term here, and the fact that the Zt satisfies an energy estimate justifies the existence, the proper definition of this. And this process here is a continuous martingale with a certain quadratic variation, and when you reverse the process, what you get is exactly this martingale, but you exchange the sign of the drift. And when you have only 1 and 3, you have an Ornstein-Uhlenbeck process. It is in this sense that we get to the notions of these SPDs that I mentioned before. And I just want to stress that uniqueness of these energy solutions, it has been proved by Gubinelli and Perkovsky in 2018. I'm done, no? Almost 1 minute, 2 minutes? Okay. So how do we do it? Let me try to be very, very fast now, but at least I want to explain the message. So we have these 2 conservation laws, particles of type A and particles of type B. I cook up a field that I call ZNT, which is this linear combination that I call D1 times particles of type A plus D2 particles of type B. Starting point is Dynkin's formula. So you have a martingale, which has these boundary terms in time, this compensator here, and now we look at the action of the generator in this new field and the derivative in time, so how it evolves in time. Because we are taking a frame, there is a contribution which is written in terms of the velocity that you see over there. And this will play an important role. Now, when the generator acts on Xi A and Xi B, we have a mixture of these currents of these two particles. So we will see some cancellations in the quadratic terms. Now we have to center these variables, and centering basically, it's going back to what mode coupling is doing. We are removing the linear part of the equation. Okay, so after we do that, some bunch of computations, we have these terms, and I just want to say that the red terms are quadratic terms. The terms in black, we kill them, we cancel them exactly by making a choice of the linear combination. Let's say you see case 1 over there. If we make the choice that the velocity and the relationship between the constants is this line is equal to 0. And also if we make this choice, and when we do this, we fix the fields. And this is exactly the same fields that have been predicted by mode coupling. So when we do this, when we make these two choices, we cook up these two new quantities, living in different frames, because these velocities are different, and now we just have to take care of the quadratic terms. So back again, we are looking at the entries of the coupling matrices. And then we say the following, 1 minute, yeah. And then we say the following. So let me just explain quickly. In case 1, you plug the numbers that you got from the previous slides. You take the velocity. You make a choice, d1 equal to 1 and d2 equal to -1, and you get to this term in red. In the black term, there is nothing to do. And now you rewrite these in terms of your quantities, which was the phi plus and the phi minus, which were either the sum or the difference of the quantities. And you do that, and you write it like that. And you see here, okay, maybe you can see here in my... that line over there, that when A is equal to 2 means that I'm in diffusive time scale, and when I take gamma bigger than a half, this term vanishes, so we only have the term, let's say, the Ornstein-Uhlenbeck process. But when A is equal to 2, diffusive time scale, and gamma equal to a half, though we can write this term as products of the fields, but the field is in a wrong frame. So in fact, and this goes back to what was predicted, that when you see these off-diagonal terms of the coupling matrices, they are irrelevant. And this is true, because we can prove that, in fact, we have this product of different terms in wrong frames, let's say, and this doesn't contribute to the limit, only contributes with a drift term. And so, again, we have Ornstein-Uhlenbeck behavior. Now, if we do the same thing for the other quantity, we get a term which is the quadratic term, so let's say the quadratic term of the same quantity, and we get to KPZ regime. So in conclusion, the limits that we get really depend on the quadratic terms and how you rewrite the quadratic terms in terms of the new quantities. And then it depends on what survives in the limit. So just to finish, because I'm really out of time, I think. So these are some references. Okay, there are many others which I didn't put here, but if anyone wants to know references about hydrodynamic limits, I can just say. And these are the 4 Bibles that I usually have in my office when I want to know something about particle systems. So if somebody wants to understand what is particle systems, I suggest that you read these books. And thank you very much. So I have to say that I wrote this here because I really don't want to forget. It is an honor to receive the Schramm lecture, a named lecture, and in this case, the Schramm lecture at the World Congress. And this is not just a recognition from the community from me, but it's from the work that I have been developing with many collaborators. And so I would like to thank you very much for your attention, for being here with me up to the end, and I dedicate this talk to these people. So thank you very much. I know.
You mind to go back to the energies, the slides about the energy solution of the Berger's equation? Mm-hmm. You mind to go back to the slides? Mm-hmm.
Yeah. You mean the definition, right?
Yep. So in the third point, isn't that you need to have some limit, or isn't that you have to define the nonlinearity?
Sorry, you have to repeat, sorry.
For the Berger's nonlinearity, isn't that you have to define it through a limit or something?
See if I have what, sorry?
Which term accounts
which term? Yes. Oh, no, sorry. Yes. The BT is the term which is related to the Berger's nonlinearity, and the fact that we are assuming an energy estimate.
BT. Oh, BT is not the martingale.
No.
This
No,
whole
BT.
this whole object is a martingale.
Yeah, the whole martingale.
Okay.
So MT is the martingale. Yeah, I didn't call MT, but MT equal to that is the martingale.
Okay.
And the BT
is the limit of something.
Yeah, exactly.
Okay.
Which exists because of the fact that the process satisfies some energy estimate.
Okay. And you have only one noise, or you have coupled the two noise?
Well, in this case here, this definition is just for one noise, but then in the other case, we have two noises for the two cases. So let me just maybe show you the theorem. And what do we know about these noises? Maybe I didn't say, but let me just go back. In this theorem, you have two noises. You see the W plus and the W minus, and what we can prove is that these noises are independent. Okay? And it's very important that, in fact, you really use the fact that you have this proper linear combination to show that the noises are independent. So you really need these constants to be exactly what we chose.
Thank you. It was a fantastic presentation. I have a question. So, could this be repeated by any other interacting particle systems? I'm not sure why. Is it really necessary just to use the WASEP? Could you start by TASEP or even inclusion process? And also, could you derive by this case other equations in the KPZ universality class?
So let me tell you what I know about this subject, because this picture that I showed here, it's not only for exclusion processes. In fact, okay, let me just show you quickly this. So I mentioned here that, it's here. This transition here that you see from Edwards-Wilkinson to the stochastic Burger's equation can also be derived, for example, with models with two conservation laws. So there are models for which one of the quantities does exactly the same kind of behavior, but there you don't tune the strength of the asymmetry, but somehow you have two dynamics and you tune one of them in order to get this crossover. Okay? Now, other equations from exclusion processes, yes. So for example, if you take long jumps, remember the case where I talked about hydrodynamic limits and we get these fractional equations? That one we can also get from here. So instead of getting let's say, the stochastic Burger's equation, we can get the fractional stochastic Burger's equation. And recently we are getting the fractional stochastic Burger, but with the regional fractional Laplacian. So we are looking at the system in finite domains. And this is probably what people in mode coupling, so there are some predictions in mode coupling that I didn't show. There is a zoo of equations. There is one which is called the modified fractional KPZ, which probably could be these fractional stochastic Burgers. I don't know, this is just maybe a conjecture.
Thank you.
But then nothing has been done. So this is a world to explore. Only these connections between Edwards-Wilkinson, stochastic Burgers and Edwards-Wilkinson Levy 3/2. Well, this week we heard Giuseppe talking about the crossover from Edwards-Wilkinson to Brownian-Kastel, but all these other predictions, and in fact they predict that you can get Levy processes with any parameter which lives in the Fibonacci sequence. So this is a mystery. I don't know, but has not been obtained. Just few of them have been obtained. Are just predictions.
Thank Patricia again for a nice talk. And the second thing is that Patricia and I decided that it's the last talk of the conference. So, and a lot of things go into a conference, from tickets on mobile phones to talks to various things. So we should all thank the organizers and scientific committee and everybody who made the meeting possible. So both of us.
And I don't have to repeat this story because everybody has heard it in the meantime. Knowledge from Ruhr University Bochum. Thank you very much for coming, Patricia.
Thank you so much. Thank you.
Yeah.
Thanks. Thank you so much.
So we need the actors for the closing. Victor, Aurora, Kavita, and Adrian. You are needed.
Just want to thank all of you for staying here, and I want to particularly, this is from Aurora and me, to really thank the local organizing committee. We just did a little bit. They took all the burden off us. In particular, Harold Daling, Peter Eichelsbacher, Christoph Kuhlske, Christoph Thaler, Anita Winter, Holger Detter, Axel Bucher, Roland Fried, and Jeanette Werner. So I want to really thank all of them. Please, a big... And I particularly want to thank also, Christoph Kuhlske and Benedikt Janel for bringing music to the program. That was very special, and let's give them a hand as well. And I also want to thank, again, Harold and Christoph, along with Frank den Hollander, for making that very special evening yesterday, celebrating the life of Ising, who is from Bochum. So this was really very apposite. So thank you again for taking the trouble. Yeah. And I really want to thank the Scientific Program Committee, which I'm not going to name all of them, but if you heard, this is just to tell you that I'm just here representing all these other people who did all the work. Thanks to all of you also for coming and energizing this conference. I think there were over 900 registered participants at this meeting, which is phenomenal.
So I know everybody wants to take your train, so I'm not going to add much more. I agree with everything that Kavita said. The Herald was exceptional. He was also very patient and persistent, so thank you very much. We made it. And thanks to the Scientific Program Committee who helped a lot, and everybody else. And it was a pleasure to get to work with you.
Likewise, Aurori, extremely. And to thank all the plenary speakers who really set the tone for this, including the very grand finale. Thank you. We'll also have a few words from the IMS and Bernoulli Society.
Thank you, Kavita. Thank you. So Peter and I are here representing the IMS and Bernoulli Society, respectively. Of course, I would have to repeat everything, and I will not repeat it again. But, of course, we owe our gratitude to our colleagues, the Scientific Program Committee, who could not thank themselves. I do think it's a tremendous amount of work. Thank you, Aurore. Thank you, Kavita. Thank you to the entire committee. So you deserve the thanks. And the local organizers. It's a tremendous amount of work. It's volunteer work, and the community works because of volunteers. It's the conferences, the awards, the nominations, the papers, the refereeing. So thank you again, even though I'm repeating myself. It has to be said. Harold, everyone, thank you. I also want to say maybe one more thing. I had the chance to interact with Peter, with Michael, with IMS leadership, the Bernoulli leadership. I think this is a golden era for the relationship between the two societies. Very beautiful things can happen when we work together closely. We both are after the same aims, and we each bring something to the table. So for me, it was extremely positive and a great pleasure to see this. And this Congress is exactly one of those great things that can happen. So thank you, Peter. Thank you, Kavita. To Michael, who wasn't able to be here. To Tony, to everyone. So I think maybe I'll let Peter say a few words, and then we can ask the organizers of the next World Congress to give us a little preview.
Yeah, exactly. So also on behalf of IMS, we're extremely thankful for this wonderful conference. According to my senses, it has been highly successful, but also there was a very good spirit here. People were very kind, and it was just a very great atmosphere. And I don't know what it takes for that, but it just happened. And it may just happen also because everything was so well prepared. And I can just repeat the thanks of IMS also, again, to all the people who worked behind the scenes, and many of these names have been mentioned. I should point out, though, that a couple of years ago, there was always the communication of Bernoulli and IMS to the local organizers. How is it going? Is there anything as an update? And we always received this absolutely perfect report. It was really astonishing, and we've never seen that before. These extremely detailed and informative reports, what's happening, what's missing, what's coming, and we were so assured this will be a great conference. Indeed, it was a wonderful conference. Now, many people contributed here, also scientifically, and of course that's the main purpose of such a World Congress. We shared knowledge. And actually, Harold even infused us with making this even more powerful. And I ask you to come on stage, Harold, and because really you are the main person, so we would like to thank you. And Harold had this wonderful thing, this perfume, which gave a wonderful smell, and this really infused us all with additional knowledge. We could all feel it. We were all having new ideas. And there's a complementary idea to infuse more knowledge. I tried to illustrate that a bit, namely Swiss chocolate would also be a way to infuse the knowledge. And I thought, because you all gave us perfume, local perfume, I give you local handmade Swiss chocolate. Thank you very much.
Thank you very much, Peter. Thank you very much. I appreciate that.
And yes, it's time now, so we're like in the Olympics. Every 4 years we have a World Congress, and the fire from here will go to Singapore. And we ask Adrian to come on stage.
Sorry, just before giving it over to Adrian, I just wanted to say I don't want to be amiss in really thanking all the green shirts, without whom I wouldn't have been able to get to any of the sessions. So please, a special hand for them. And also all the people in the Mensa, all the people, sort of the invisible people working, whom, then the nameless, they're actually the pillars on which we all stand. So thank you so much. You can, all of them, yeah. Over to Adrian.
Okay, I don't want to say much, prolong this any more than necessary. You see the details on the slide. It's a great honor to host the next World Congress, that this is being entrusted on us. You see the supporting bodies on the slide, NUS, a few departments, Singapore Tourism Board, and I hope to see you in 4 years' time.
No long speech, so thank you very much for coming. Thank you very much for participating, giving talks, participating in the discussions. It was great to have you all here in Bochum, and I wish you a safe trip back. But before we close, I want to say something to Adrian. You have to come back. Sorry. So if this would be on a soccer field, I would now take off my T-shirt, but my daughters are watching this, so I'm not going to do that. But here, you get the T-shirt from us.
Thank you very much.
Okay. Have a safe journey back.